in the same, same area. So what is happening that when you try to do this compute, you do not get the same kind of compute capability. You may not have the same GPU, may not have the same accelerator, and there are some challenges when you want to use different kind of compute devices. And so we're looking at at all this problem both from theoretical point of view, and we're also doing implementation. So we take it back to the system and check if our ideas are working. And the last but not the least, we're also working on mobile and edge computing. So we're looking, so whenever you have a new technology coming in, like from 5G you go to 6G, and hopefully you'll have 7G. So the cost of transition is very high. So we are trying to see that if you can come up with, the higher level protocols which can seamlessly make you transfer without you having to do much changes in physical layer radio access network. Okay, and there are some other problems which are working on edge compute orchestration. Feel free to chat with us if you're here. These are more of the details about these problems. I think I'm not gonna go much into detail. And I think because we're running out of time, so I'm here, and if there are any questions, I'm happy to answer. Including from where is the food, to that I'm interested in knowing more about the center. So just one more announcement before we begin is that we're going to have a photo session just after the end of the first set of lectures, right, before we break for coffee. So we'll go outside to the EC department, and then we'll have a picture taken. Yeah. All right. With that, let me invite Professor, P.N. Karthik, who is also one of our alumni, and now he's a faculty at IIT Hyderabad. So Karthik. So we have one more thing before I leave is that because we are really tight on schedule, let's try to keep our talks 20 minutes, and if you guys exceed the time, I'm going to come and stand here. That's your cue. That should wrap up. Okay. Thank you. Thanks, Karthik. Karthik as a, so I don't know, many of you don't know, but I don't think I taught you random process, but he was my star TA, okay? And the teaching evaluation ratings are always higher for Karthik than for me. Okay, that says something. Okay, so Karthik is an assistant professor in Department of AI at IIT Hyderabad and was previously a research fellow in the Institute of Data Science at National University of Singapore with Vincent, right? With Vincent. And he earned his PhD and MS dual degree from EC at ISC, which I already mentioned several times. The research focuses on probability, statistics, reinforcement learning, and multi-arm bandits, and he was a recipient of 2026 ANRF Prime Minister's Early Career Research Grant. So please join me in giving a warm welcome to Professor Karthik.
Thank you very much. I hope I am audible. Yeah. Okay. While that is being set up, I want to thank the organizers for the invite. It feels very good to come back now in a different role, standing on the other side of the classroom. The workshop has been very conveniently timed to make it convenient for my collaborators in Singapore to watch the talk. So thank you for that also.
They're seeing a black screen,
Huh?
right?
Yeah. All right. So This is a piece of work that I did in collaboration with Rachel, who is a PhD student with Vincent Tan at NUS, and with Ramya from University of Wisconsin-Madison. This work was presented earlier, that is last month at ISIT by Vincent. So I am now going to delve into the details. Let's just dive in. So the problem is of clustering a group of items without knowing how many clusters are there, and by only obtaining pairwise feedback. So let me make it more precise. There are m items. M is of course known. Items are given to us, and each item belongs to one out of k clusters. K itself is unknown. We don't know how many clusters are there. In the example, there are 6 items grouped into 3 clusters. Clusters 1 and 2 belong to cluster 1. Sorry, items 1 and 2 belong to cluster 1, 3, 4, 5 belong to 2, and so on. Oops, okay. At each time, we get to query 2 items, I and j, and we get to present it to a noisy oracle, which is going to tell us something about whether those 2 items belong to the same cluster or not. So we get a binary reward, and the distribution of that binary reward is Bernoulli P if I and j belong to the same cluster, and it's according to a Bernoulli Q if I and j don't belong to the same cluster. Okay. So the oracle is not perfect, it can make mistakes, and the probability that it can go wrong if I and j are in the same cluster is 1 minus p, and the probability that it can go wrong if I and j are not in the same cluster is q. Okay, so a binary reward of 1 is an indication that the oracle is telling us I and j probably belong to the same cluster, and 0 is the oracle telling us I and j probably don't belong to the same cluster, and p and q are unknown. Our goal is, based on the feedback that we receive from the oracle, we want to identify the correct clustering with high probability. Okay, we want to recover the underlying clustering. No, not necessarily. So this is the problem. We get to query pairwise, items pairwise, and then we get binary feedback about whether the items that were queried belong to the same cluster or not. And we want to recover this as the underlying clustering. This is not given to us, only the items are given to us. We want to recover the underlying clustering. So the problem can actually be summarized in the form of an adjacency matrix which captures the dependence between items of whether they belong to the same cluster or not. If you see a 1 in this adjacency matrix, it means those items belong to the same cluster. Item 1, so the diagonal entries are considered to be 1 by convention, and not only does the adjacency matrix capture the full problem, the problem is also determined by the values p and q with which the oracle outputs 1 or a 0, depending on whether the underlying items are in the same cluster or not. So this is the complete problem instance for us. Okay. We are not really interested in recovering the full instance. What we are interested in recovering is only the clustering structure. So this is the backbone that we want to recover. This is the meat and the flesh that make up the problem instance. Okay. So our interest is only to recover this, not the exact instance matrix, but the values of p and q do affect how many number of queries are needed to recover the underlying cluster. Yeah, we get to ask the oracle. We can pick a pair of items.
But so suppose you have, I don't know if you're being honest, suppose you have seen like X, some number of objects so far, right? And the new object you get to see is it same as the previous one or anything, or what do you get to ask?
No, we get to ask, given a pair of items that I pick and give to the oracle, I ask the oracle, do these items belong to the same cluster? Yeah, we get to choose the pair. That's the adaptivity. Yes, for that pair we get to ask the oracle. Oracle can give us wrong answers also. No, P and Q are not known. And we say that 2 instances are equivalent if their adjacency matrices are same. So we only want to recover the matrix in that sense. We only want to recover the clustering. We are not really worried about exactly identifying the P and the Q. Okay.
What's the difference between the instance matrix and the adjacency matrix?
So the instance matrix is just P times adjacency plus Q times 1 minus adjacency. So it's just that. but really we want to recover the underlying clustering. Okay. So here if you see a P, it just means that those two items, the oracle will say that those two items belong to the same cluster with that probability. Okay. And if you see a Q, it means that the oracle will say that those two items belong to the same cluster with probability Q, even though they might not be belonging to the same cluster. Okay. So this is how I visualize the space of all possible instances in this problem. Okay. Our true instance, which is that instance matrix that I showed you on the previous slide, is somewhere in this space, and there are many other instances which have the same skeletal background, the skeletal backbone as that of our true instance, but with different PQ values. So that's this blue square that you see, and the other squares that you see here are instances which have different clusterings itself and with different values of P and Q. So there are uncountably many instances partitioned into a M-fold partition. Within each partition there are chunks representing equivalence classes based on the equivalence relation that I showed you earlier. Okay.
And what is your objective?
The objective is to recover this blue box. I mean, we only want to pinpoint saying that the instance lies in that blue box, even if we can't pinpointedly identify the instance within the blue box. Can we nail down the blue box? That's the clustering that we are after. Rather, the entire, so this is the exact clustering that we are after. Okay. Now, some of you may know stochastic block models.
One question.
Yeah.
But in C, sometimes it might happen that you might get in C4, but you are actually pretty close.
Yes, yes.
So I mean, it's not necessarily C3 is what I should aim for. I should try to get adjacency matrix right, but one person I got it wrong. It'll land up in another.
That's not allowed. We have to recover the underlying clustering exactly. So it's going back and okay. So our setup is slightly different from a stochastic block model, if some of you may know from community detection problems. So there, typically one random snapshot of the entire graph is given to us, and from that random snapshot we are supposed to recover the underlying clustering, whereas here we can actively query what pair of items to ask the oracle information about. So we can choose what edges we want to uncover in the graph. Whereas there, one random snapshot is given to us, we don't have a control over what edges are shown in that random snapshot. Okay. And typically in SBMs, the notion of asymptotics is by letting the number of items or the number of nodes in that graph go to infinity. Whereas for us, the number of nodes or the number of items is going to be fixed, and we will look at the error, the probability with which we are going to recover the clustering. We are going to let that error go to 0, or we want the accuracy to just go to infinity. That's the notion of asymptotics for us. And in SBMs, people usually study about the recovery guarantees under conditions when the P and Q edge probabilities scale with M as log M over M. That means they vanish. Whereas for us, P and Q are fixed, unknown, not known to the learner. Okay. So whatever I'm going to describe henceforth will be from the perspective of a learner. Let's say all of us are from the perspective of the learner. I'll try to describe the problem from that perspective. Okay. Now, if you want to identify the true clustering, which is that blue box, you have to rule out all the incorrect clusterings. That's as simple as that. So to formalize this, I introduce the notion of an incorrect clustering. Okay. So let I be the pair of I be the set of all item pairs without any specific ordering, and let Pi be the probability distributions on I. The underlying instance is going to be represented with C. That is the matrix, PQ matrix that I showed you, unknown, completely unknown. Okay, neither is the skeleton known nor is the meat and flesh known. The set of alternatives for this clustering is all other instances which get the clustering wrong. Either they get the clustering wrong or the number of clusters itself wrong. Okay. So in C there is a particular skeleton and there are k clusters. Let's say all other clusters come and all other instances come under alt C. So these are alternatives. We don't want to end up identifying one of the instances in alt C as the correct instance. That will get us a wrong clustering. We don't want this. We want to battle this. How much is the effort that's needed to battle this? Well, you can derive an information theoretic lower bound on the number of queries that you will need, okay, to identify the true clustering with high probability. So if delta is the probability of error that is allowed, information theoretically, by using data processing inequality, we can show that the expected number of queries that are needed to recover the true clustering C with probability 1 minus delta is going to be a quantity like this. Notice that the numerator blows up as delta becomes smaller and smaller, and that is also intuitive in the sense that smaller the error room that is allowed to recover the exact clustering, larger would be the number of queries that you would need. And the constant that appears in the lower bound has the interpretation of a game between learner and nature. What can we do as learners? We can choose what lambda to sample the items from. Okay, lambda is a probability distribution on item pairs. We can pick an item pair at every time instant according to some lambda. Usually this is done in order to maximize some information gain. Okay, and nature will present the most confusing alternative to us to minimize the information that we gain out of the system, and this game somehow captures the amount of the hardness of the problem. That is, how much of effort do we have to put as learners to identify the true clustering while nature is trying to confuse us along the way. Okay, we have to battle against nature. So this is what happens. Now this is well known for people, for some of you who may be working in bandits, best arm identification and so on. This is quite standard. But one of the novel things that we show is that the inner infimum here can actually be reduced in a very nice way. Okay, so there is a minimal set of alternatives that it comes down to. On the left side, alt, as I said, is the set of all incorrect alternatives. Like these are all alternative instances in which either the number of clusters is wrong, or the clustering itself is wrong, the skeleton itself is wrong. But what we show is that you don't have to battle against all of them. What you have to battle against are only those clusters, or rather those instances, in which the number of clusters is either one more than the number of clusters in the true instance, or one less than the number of clusters in the true instance. Even more specifically, those that will cause a problem to us and those that we have to battle against are those instances which are either obtained by splitting a cluster in C into two, one-step split, or a one-step merge of two clusters into one. Okay, so here is the true clustering from the picture I showed you on the first slide. This is a clustering that is obtained by splitting this 3, 4, 5 into 3, 4 and 5. Okay, similarly, if you merge this 3, 4, 5, or rather 1, 2, 3, 4, 5, you get this merged cluster. Clusterings like these, what the theorem says is that clusterings like these are the most difficult to distinguish. Okay, now you might wonder, why is this actually true? Okay, in a couple of slides I'll try to explain the intuition. So what happens is, let's say C is this and C prime is this, some other alternative clustering. Notice that the number of clusters in both are same. Okay, that's not what we want. We just don't want to identify how many clusters are there. We want to identify the clusters exactly, the skeleton. Now what happens is, when we go from C to C prime, one way to go from C to C prime is break 1, 2 and then break this 3, 4, 5 and then merge some of these to get this. Okay, now in this process what happens is, you can keep a count, you can keep a track of what items were together in C but got far apart, further apart, got separated in C prime. So okay, that's N1. N2 is what items were separated in C but came together in C prime. Okay, that's N2. Okay. Now what we can show is that the inner infimum in the expression that I showed you can be written as a minimum over finitely many alternative equivalence classes of some function of these N1, N2 masses. Okay, the exact expression here is not important. The important point is that this Z happens to be a non-decreasing function of the probability weights on the sets N1 and N2 under any probability vector lambda. Okay, this relationship holds for every probability vector lambda. Okay, so what happens is, if you look at C versus C prime, N1 is this. But if you look at C versus this instance 1, which only happens to be one split away from C, then you can show that N1 is just this much. Similarly, N2 is this particular quantity between C and C prime, but between C and 1, which is just one split away, like I said, N2 is just an empty set. Okay, so if you look at the total mass that any probability vector will put on this set, it's going to be this, whereas the total mass that that same probability vector will put on n1 of C1 is just lambda 1, 2. And it doesn't take any great minds to figure out that this is smaller than this quantity, this is smaller than this quantity. So the z applied to these two quantities together is going to be smaller than the z applied to these two quantities together, simply because z is non-decreasing. So it is the z that is being infimized, okay, and the infimum will naturally be achieved at such clusters 1 where either they differ by a 1 split, or similarly you can show for a 1 merge also. So just 1 split away or 1 merge away, those are the clusters you need to be really worried about. Okay, so this simplification actually helps us make the problem amenable to analysis, and it helps us design a very effective algorithm. So what's the algorithm? So now I have described the lower bound. I have told you how many queries are needed on an average. What is the least number of queries that are needed on an average? Is there any algorithm that we can design to identify the underlying clustering itself? Well, we don't know the underlying clustering, we don't know the instance, we don't know the skeleton, we don't know P and Q. Well, estimate it. You have observations from the oracle, estimate it. Some observations are incorrect. The oracle is noisy, that's okay, just estimate it. Estimate the underlying instance. So this is the empirical instance, and one would imagine we can just plug in the empirical instance into the expression for the lower bound and get the set of all optimal allocations, you know, for this particular empirical instance, and one could simply sample the next pair according to any vector, any probability vector in this set of optimal allocations. Well, if it was so simple, I wouldn't be here. The problem is that this doesn't work because the instance C that I showed you, the matrix C that I showed you, has only two kinds of distinct entries, P and Q. Okay, whereas a typical C hat will look like this. You can't make sense of what is the P and what is the Q. There is no one P and one Q in this. There are so many entries, right? So this is the problem. We need to somehow extract a valid instance from this. This is not a valid instance. We need to extract a valid instance in which there are only two distinct entries, P and Q. So how do we do it? We do a projection. Okay, what projection is this? 4 steps. First step is we threshold the values which are more than half to 1 and less than half to 0. So this will give us a binary matrix. The problem is that this binary matrix may not actually be a valid instance, a valid skeleton, a valid clustering, simply because, notice here, after thresholding all the values above half to 1, we have ended up with this matrix. According to this matrix, 1 and 2 are in the same cluster, 2 and 6 are in the same cluster, but 1 and 6 are not in the same cluster. That cannot be a valid instance. So you need to find the instance which is closest to that instance, okay, and that we do using this L1 metric. So we find the instance, we find the matrix, the skeleton matrix, which is the closest to that particular thresholded matrix. Now this C tilde is a valid skeleton. Okay, we still need to fill in the flesh and the meat. So the flesh and the meat are simply obtained by taking the average of all the entries which are above half and the average of all the entries which are below half, weighted appropriately with the number of times each ij pair has been observed up to a certain time t. Okay, each of these entries has been obtained based on different number of queries, different number of observations, right? So you have to appropriately weight them with how many times each query has been observed, how many times each pair has been queried, and so on. So those are the expressions. Once we do that, with the skeleton and the flesh and the meat, we just combine and get the actual instance. So this is called a projected instance. This is a valid instance matrix. Okay, so the idea is that we use the valid instance matrix to come up with a probability distribution according to which we can sample the next pair. This is just mixing that probability distribution with uniform to make sure every pair can be queried with a positive probability at every time instant. And we use what is called the standard detracking algorithm or the track and stop algorithm of Garivier and Kaufman to sample the next pair. So if we do this, we can show that the average number of times or the fraction of times every pair is queried approaches the optimal proportion. Okay, approaches this optimal proportion. Notice that here it is Ct, but in the end it is actually C. Okay, so it approaches the correct proportion that it has to approach. Okay. Now a natural stopping rule, that is you are querying, you have to stop at some point in time. So a natural point of stopping is to construct a test statistic and just let the test statistic exceed some appropriate threshold and see if this can be a valid stopping rule. Now this test statistic that we are using is the standard GLR statistic. So if you do this, one can show that this stopping rule will output the correct answer with high probability. Remember, we have to identify the clustering exactly, not approximately. Exactly we want the clustering precisely, and with high probability we are able to recover that exact clustering. And with that GLR based stopping rule and the detracking rule that I showed you earlier, we can show that the upper bound will be something like this. Now this is the information that's gathered under the optimal sampling rule. If you were to sample at every time instant according to this lambda star probability distribution, and then there is a regularization penalty just to make sure that we end up with a unique optimal solution at every time instant. And the important point to note is that this constant approaches the constant in the lower bound. So the lower bound is governed by 1 by d star, upper bound of the algorithm is governed by 1 by d epsilon star. You can tweak epsilon and sigma to make the upper bound arbitrarily close to the lower bound. So asymptotic optimality is established. Okay. One more point that remains to be said is that the algorithm that I told you about, that is the GLR stopping rule, is not easily implementable. Okay. Solving this optimization problem is quite tedious. Okay, for the reasons that there is CT here, whereas what is there here is not the probabilities PT and QT under CT. Okay, these are some other probabilities. Even if you replace them with CT and QT, it's not going to be very easy. Okay, you lose some delta correctness properties and all of that. So the point is that you have a statistic that doesn't have a closed form expression and it's difficult to implement. So what we do is we simply factor out the minimum quantity from that expression. Okay, this is a very naive tweak, you can say, but it somehow works. So we do a minimum factoring, and then whatever comes inside this KL can be easily evaluated. That much I can promise you. Okay. Now the associated stopping rule with this is tau hat, which is wait until this test statistic exceeds the threshold. So what's a big deal about this test statistic? Well, because you have factored out the min, this is obviously smaller than the original test statistic, and because the original test statistic, with the original test statistic we have delta correctness, even for this we will have delta correctness. So delta correctness is somehow preserved. Okay, and with that new modified stopping rule, we will have an upper bound that's of this particular form. Okay, with the min that is coming here by as an artifact of the min being factored out of the test statistic. So this is the minimum sampling proportion, this is the overall KL separation, there's a regularization penalty, and this packaged together is our algorithm, which is called almost asymptotically optimal active clustering with noisy pairwise observations. Except for almost asymptotically optimal, the rest of it is my talk title. So I hope I have clarified it. Okay. Now of course there is a gap between the upper bound and the lower bound of the modified algorithm. The GLR based stopping rule achieves the denominator as the lower bound or as the upper bound, whereas the numerator is the upper bound coming from the alternative stopping rule. So there is a gap between the two, but what we are able to show is even if we can't estimate the gap precisely, we can get a very, very good upper bound on the actual gap. Okay, and in practice we can estimate this by using a proxy on the way. In the algorithm itself, while we are running the algorithm itself, we can maintain a proxy for what is this upper bound. Okay, so we have a hold of how far away our upper bound and lower bound are from each other. Okay, and we ran some experiments. We are also augmenting these with some more experiments in a future version. So we see that the algorithm that we have designed significantly improves over an active clustering algorithm that was proposed in an earlier paper. Okay. So these are just experiments for the same setup that I showed you earlier, the first picture that I showed you. Yeah. So what we have studied is a fixed a noisy pairwise clustering problem posed as a fixed confidence bandit problem. Okay, this is why fixed confidence bandit problems are ubiquitous. Okay, they come in all places. It's a very important framework to be aware of. And then we derived an instance dependent lower bound on sample complexity, and we proved that the algorithm that we designed is near optimal. And we have achieved the figure that I showed you at the beginning. I have completed it with our algorithm A-cube CNP. So for more details, you can please look at our archive paper. Thank you. Yes.
Yeah, so in the HBM literature, there is this understanding that if you take a matrix, not adjacency matrix, but a matrix of self-avoiding ones of certain length, and you do spectral clustering, then the eigenvalue structure will sort of tell you where the clusters are. That's how the proofs generally go. So is there any connection to that kind of spectral understanding and the way your algorithms query and process things, or it's completely tangent?
Yeah, so the matrix itself is not known to us.
Yeah.
The underlying matrix is not known to us. So our idea is to recover that underlying matrix, the skeleton.
You can get the average thing which you had, right? That could you
Do some eigen analysis
I
and
don't
so
know,
on.
I'm just saying what
Yeah, that's a interesting.
I'm not adding anything.
Correct. No, I understand. We have not tried that, to be frank, but maybe it might be worth exploring, especially for a slightly more difficult situation where the probabilities are not just P and Q, but are maybe P I J Q I J depending on the items that are queried, right?
I think the problem with that approach is, Shanmugam, is the eigenvalues may be not very robust to changes, right? Because you still
No, that's why you do the self-avoiding ones, where people show that you can get to the information theoretic limit of whatever you can identify. Like however close to just log m by m, right? So it's not just adjacency, but you have to do self-avoiding ones. You have to count how many times you can walk and come back to the same point without by avoiding any particular node twice. Right? So you count the number of walks and you put those entries, and then you do it.
Okay.
But anyway, we can.
Interesting conversation, but you are the next speaker, so you take in your own time. Before we go, hold on. So, global appreciation from SPARC and CNI.
Thank you. Thank you so much. Oops, okay. So is this the PDF or the PPT? I have. So is it possible to use the PPT? So I have one animation to show. Not that it's super important, but I upload. Yeah. Slideshow. Yeah, I think it's fine. It's a GIF.
Our next speaker is Dr. Karthikeyan Shanmugam.
The PPT shows up
He will
in
be
the
speaking
slideshow.
on efficient approximate posterior sampling via annealed Langevin Monte Carlo. Dr. Karthikeyan Shanmugam is a research scientist at Google DeepMind India and was previously a research staff member and Herman Goldstein postdoctoral fellow at IBM Research. He earned his PhD from UT Austin and his BTech and MTech in electrical engineering from IIT Madras. His research focuses on causal inference, online learning, and foundation models. Dr. Shanmugam is a recipient of the 2021 IBM Corporate Technical Award for his work on trustworthy AI. Let's welcome Dr. Shanmugam with a big round of applause.
Yeah. So thanks for inviting me for this wonderful workshop. So it's also good to see a long time old colleagues like Salim and so on. Thanks for having me. So this is a last minute change in the title and the abstract because I realized it's only 30 minutes. If it was the other talk, I wouldn't be able to convince you that the problem is important. So this one is much easier. And Parimal explicitly asked me to talk about generative modeling because that at least is closest to the learning part of the workshop, although there is no distributed aspect nor optimization. So I'm going to talk about mixed mode, discrete continuous diffusion for the applications are molecule generation and layout generation and so on. So it goes beyond the typical generative modeling that you've heard about over LinkedIn and Twitter and so on. You know, there's like a blast of news all the time about text models and image models. So here we are going to talk about slightly a very different kind of generative modeling that people care about in the sciences, for example, or in engineering for that matter. So this is joint work with my colleagues at Google DeepMind India, Dheeraj Nagaraj, Gautam Govindanil, Sachin Yadav, and myself. And I should say that
lion's share of the work was done by the students, Gautam, Govind and Sachin, who actually patiently coded up all the things that we asked them to code up, apart from actually critical ideas in this paper. Okay. So the outlines of the talk is, I'm going to introduce a very general framework for generating discrete continuous data together when they are actually very tightly coupled, and I'll tell you examples of why you would need something like this, and this would be the end of the talk, like what this framework is. Essentially the reason you want to do something like this is because in many cases you want to generate not just text like tokens and not like image like tokens, but you want to generate both of them simultaneously, and if you change even one discrete token, it would actually affect the continuous part quite heavily. Okay. So for example, molecule generation is one example. So you would like generative models that can actually seamlessly noise and denoise and actually generate discrete continuous mixtures in a seamless way. So the question is, how do you actually do it? Because continuous diffusion is its own field, it has its own theory about how to noise and denoise, and discrete diffusion is its own field and it has its own techniques about how to noise and denoise. So the question is, if you have to do something jointly, what is the simplest way in which you can actually do? So there is a technical tidbit, but if you are not familiar with continuous diffusion, this is probably not very important. Just saying that we sort of generalize some of the theorems people use in noising and denoising in continuous diffusion, and I'll show you some very nice animations about how this actually works. Basically you can do SAT solving, like constraint problems, which autoregressive models cannot do unless you actually put in a lot of compute. You can also do molecule generation, you can also do chip layout generation and things like that. Okay. So I'm just going to show you some demos of what we have done. Okay, so let's start with continuous diffusion, which is one of the modes that I talked about. So usually how it works is that you take an image and you slowly destroy it by simply convolving with Gaussian, okay, at some rate. Okay, so you just add Gaussian, normalize, add Gaussian, normalize, add Gaussian, normalize until everything becomes completely grainy. Okay, so you construct a Markov chain, and the way you reverse this, reverse this process is that you start from a Gaussian at test time, which means somebody is actually given you a prompt and you want to generate an image like this. You basically start with Gaussian and then you sort of follow this ODE back, which is effectively basically reversing this Markov chain. This might look a bit scary if you are seeing it for the first time. The most important term is actually this grad log PT. What this means is that suppose you are in this grainy cycle, it's asking itself in an expected sense, what is the direction in the high dimensional space I would like to move. Okay, and grad log P of xt basically says roughly in which direction you would like to move, right? And then you just move along this direction and so on and on and on until you will actually get a denoised image. So the theory for all of this has been worked out 35 years before. It's just what is fancy is the application of that in actual generative modeling with transformers and stuff. Okay, but keep this in mind that you are just destroying using Gaussian and then you are just reconstructing it back by reversing a Markov chain. So that's all I want you to understand. Now text diffusion, actually the question is not yet settled in either academia or in industry. What is the right noising and denoising process in the discrete space? What's the right denoising learning principle? Unfortunately, it's not very trivial like the one that I actually told you in the continuous space if you want speed. But there has been quite a lot of work. In fact, DeepMind released an open source model. You can all use it if you want, and you can even see how it actually generates and so on. The code is available. It's called Diffusion Gemma, and there is also other like diffusion models which are enterprise grade by other labs like Inception Labs and so on. This is by Stefano Erban. So it's a very active area of research how to actually do the noising process in discrete space and denoising in discrete space. But one thing I can assure you is that it looks nothing like this. It's not like adding Gaussian and then trying to reverse a Markov chain. Okay, but autoregressive models dominate still, but that's another side note. But in mixed mode diffusion, which is the subject of today's talk, I want to do both at the same time, and the continuous parts very strongly couple with the discrete parts. So I'll give you an example, but before the example, I just want to say that all the commercial models that care about continuous diffusion or discrete diffusion care about speed, because they want the answer as quickly as possible. In fact, that's something that they would all advertise. But in science and engineering applications, you generally would like to produce some discrete tokens because you could be designing a chip.
where you would like to know what components to place where. Okay, the where part is actually a continuous variable, but the what part, like the memory component should go there, maybe something else should go somewhere else, maybe the MXU unit must go somewhere else, and so on. Those are all discrete components. I mean, there are not that many, right? So you can think of a chip layout as actually a sequence of discrete tokens followed by some continuous tokens in some suitable encoding, right? So how do you generate discrete continuous coupled data? And that's really what I'm going to actually talk about. And there are many examples like this: SAT problems, molecule generation, chip layout generation, and so on. Here speed is not important. I only want quality. I mean, I'm not an engineer who's just looking at whether I can get a chip layout which is really good within a second or 10 seconds or 1 minute. It's okay if it takes even 1 hour and gives me an actual good chip layout that I can actually deploy, right? So okay, the main result is this. If you even take away this particular thing and read my paper, I think I would be very happy. So we interleave any arbitrary continuous or discrete noising denoising process with a meta approach. Okay, so you give me a continuous denoising process, you give me a discrete noising and denoising process. I have a way in which I can interleave both and do a meta overlay. So what is that meta overlay going to be? It is actually inspired by one of the simplest Bayesian algorithms that you get taught in your graduate school, which is basically Gibbs sampling and Ising models. So in Gibbs sampling and Ising models is that I have a joint distribution over Boolean variables. If I want to sample from this distribution, what do? You take the conditional probability of every bit given all other bits, and then in round robin fashion you just keep flipping with respect to this probability, and then you will slowly eventually converge to the true distribution. Of course it has mixing time issues and all of that. Our approach doesn't have any of that, so I'll have to tell you how I modify this general principle to actually do continuous and discrete denoising together. But before I start, let's start with text diffusion itself, and let's start with how Gibbs sampling can be directly applied to generate text. Okay, so this is one of the earliest models that people actually built called masked language models. The way they are trained is you take a sentence, I mean I'm just showing it in characters, but usually it's words. Let's say the training will look like as follows. You randomly mask some position, and then you ask the model, a transformer model, to predict what this missing piece would be. Okay, so it's basically a conditional probability law that you are training, okay, again and again and again over lots and lots of data. So if you have a conditional probability law, I actually told you you can do Gibbs sampling, and then you can try to actually sample from this distribution, and hopefully you will get text. It turns out you can do that. Now you can keep doing round robin, you can keep doing round robin, you can keep doing round robin, and I mean this is an empirical result on some data set where you can actually show that after 128 rounds you will still be a bit very far off from what you can achieve using the technique that I am going to actually tell you. So Gibbs sampling works, but it takes a very long time before it can actually generate some reasonable text. By the way, this is already a very powerful model used in embedding and all of that, which you guys use in retrieval today. But the point is, if you try to use this to generate using Gibbs sampling, it's going to take a long time. Okay, so the first thing that we are going to do is, how do I basically speed up Gibbs sampling for generating text in the first place? By the way, by all enterprise grade diffusion models out today, even the method that I am going to describe to you is very slow. Okay, so people do something very fast, but my intention is not to take you to fast things, but this speed is too bad. But my intention is to actually just move on to discrete continuous problems, and this generalization is very useful. Okay, so how do you actually do the noising process? So you have a round robin sort of a permutation order by which you process tokens. You can say at most 4 rounds or 5 rounds or 6 rounds. For text, 4 rounds actually work in practice. So you do the following simple thing. When you are processing a particular token in round robin fashion again and again, you replace it with a random token with probability pt. Okay, and note the most important thing is the probability is a function of time, which round you are at. Okay, or just leave it as it is with probability 1 minus pt. You move or you don't move with some probability that is a function of time. So that's all I'm going to do. This is the noising process. Now how am I going to denoise? So for example, the noising process will look like this. Green indicates I have just left it as such, red indicates I have actually flipped. So let's say you take these 2 times where nothing has actually happened. So essentially you have just a transformer that basically tries to predict like what would have been this particular so you can actually put E also here, and then you can try to predict E itself. but if you are between say this time and this time, you actually change the n to z. So you would like to know if it was k e z e r a t, what was actually the previous denoise state. So essentially from a more noisier state, you are trying to estimate what the previous denoise state is, but only at the symbol where I processed it, okay, and that's a deterministic order. So at any point in time I don't know which token I have to worry about, and in basically when I am trying to infer, I just reverse the process. I start here, which would be at the end of time, and I know which position I have to process, which will be reverse round robin, and then I ask myself what should this token be, and then the transformer will just slowly start predicting, and then you do multiple rounds and you will probably get good text essentially. So it turns out that if the noising process can noise, basically go to completely random tokens or go close to completely random tokens with a TV distance of epsilon or whatever, right? Then what you can show is within exactly that time, if the transformer was accurate, that it was actually jumping from one denoise state to an even more denoise state, then this can actually mix in finite time. Okay, there is no finite time, in fact exactly the same time that you would have taken for you to noise. So when you change Gibbs sampling as a time dependent thing, because the law that I will use to basically predict the token here is very, very different from the law I would use to predict the token here, because here most likely the sentence is fully formed and you made one mistake. Here the sentence is yet to be formed, therefore you can make it you can make it start with anything useful basically, right? So the law is very, very different. So once you make the Gibbs law very time dependent and couple it to a noising process, effectively you can mix very fast. So this is the first idea. So if you understood this, at least you would know how legitimately you can do discrete sampling properly. Although it will take 4 times the number of tokens you want to generate, which is still slower than what autoregressive models would do. Okay, so this we already saw. So now I'm going to switch gears and say that the real problem that I'm going to talk about is you have discrete part, which I told you how to do using Gibbs sampling, and there's this continuous part, which is usually done with Gaussian noising and denoising, right? So, but you have problems, for example, molecules, let's just take molecules. So molecule is effectively represented by a sequence of atoms that are there in a molecule, carbons, nitrogen, oxygen, and so on. And you have to tell what are the bonds between the molecules, sorry, the atoms in your molecule. And then you have to tell me in 3D space, where are the atoms located with respect to each other. So if you encode the entire thing, the first set of things that I told you, atoms and the bonds, would be discrete, and the second set of things will be continuous, okay? Now I told you how to do discrete noising and denoising, and I showed you how to do continuous noising and denoising. So the question is, how are you going to do both, right? And actually generate in finite time. So all these, by the way, there are other examples. For example, there are user interface layouts, which is like, let's say you are making a website. There are some text boxes, there are some figures, and there's some chat window, and you have some space for advertisement and so on. Humans tend to place them in some specific way so that it is very aesthetically pleasing, or it's business friendly, or whatever. So if you have enough samples of them, can I actually generate a layout without humans intervening, right? So you can actually fit a generative model. Chip layout would be an example of that also, you want to solve such problems. The most important criteria in all these problems is that the moment you change one nitrogen atom, so many things will change. Maybe your valency will go off, which means you have to change other atoms in your molecule to make it a valid carbon molecule, and then you will also have to change how the nitrogen is placed in 3D space. Maybe oxygen and nitrogen are probably, if they have a bond between them, probably they're closer to each other with instead of, for example, if you have a bond between carbon and nitrogen, right? So you might have to change the continuous part dramatically. So you will have to really worry about, if you change or flip something, you will have to actually do something to the continuous part also. And if you did something to the continuous part, then probably it doesn't correspond to the atoms that you already started with. So you'll have to change them and so on. So you want a process that can do all of this, right? So we are just going to pretend all the continuous tokens are some other equivalent of discrete tokens, but with an unknown, like, a denoising process. But when we hit that token, we'll actually do what continuous noising would do, but partially. Like, we won't noise it fully, we will just noise it partially. So that is the main idea. So what you have is, you have the same round robin thing, but this is a first continuous token, then there's a discrete token, then there's continuous, discrete, and so on. I'm just showing it in a very simple interleaved pairwise order. You do this round robin stuff, but then you also do the same thing. So So whenever you hit a continuous token, you always do some noising, but how much of noising you do is basically controlled by this beta. Okay, so there's a quantum that you noise. So you don't noise it fully. So it's equivalent to this move or not move, the discrete style of actually noising. But when you hit a discrete token, you have both choices. You either leave it as such with some probability p, or you actually move with probability 1 minus pt, and then you move on. So what essentially happens is, here whenever you hit a continuous token, you're just adding more Gaussian noise. So eventually everything will become Gaussian in the continuous parts. In the discrete thing, at least at some point you would touch and flip that, which means it will become a random token. So finally you will actually get a completely random set of like Gaussians with just a product distribution with just completely random discrete tokens. Now I have a Markov chain. Now I want to reverse it. Okay. So this is basically in math. So if you have discrete tokens, so with some probability, you basically make it a completely independent member of the vocabulary. The vocabulary is given by the distribution pi t, and zt is this random token that you're sampling and putting it there. Sometimes you just leave it as such, but in the continuous space, you actually do this stuff a little bit more. I mean, I've just shown it as one combination, but you basically have to do it a few more times. Okay, and you do a gradual noising, but you don't fully noise it, which means beta doesn't go to 1. That's all I'm trying to say here. The reverse process is whenever you hit a discrete token, whatever you would have done in the discrete process, just try to do that. And when you hit a continuous token, whatever incremental denoising you would do in the continuous token, you basically do that. I mean, there is a little bit more as to how I actually do this. I'll skip that in the interest of time. But one thing I want to say is that in continuous denoising, usually in text to image, the conditioning part is usually fixed because you give a prompt and the prompt stays the same. Therefore, in continuous denoising, there is a relationship between the instantaneous score function that I actually told you about, grad log p, and the amount of noise you added till now to come to a partially denoised state. So you basically estimate how much noise you have actually added, in what direction you have actually added to come to this particular state in an MMSE sense. So it turns out that is exactly equal to grad log p. This used to be the older theorem. It turns out that we can generalize this theorem under our framework even when the conditioning things are actually changing over time, because you might have gone to other discrete stuff, change them, and then come back. So the conditioning has actually changed, unlike T2I models, right? But still this theorem actually holds with respect to the noising process that I actually told you. So that's a non-trivial part, but that's not pretty obvious, but it's very easy to prove once I tell you. I mean, it's not very difficult to prove. So I just want to show you some pictures. So this is a SAT problem, fully discrete. So you give a bunch of clauses. This is the conditioning information. You have a bunch of bits. You would like to satisfy all the clauses. Okay. So we basically just noise the entire true assignment down, and then we try to denoise. By the way, I'm just showing it on a novel clause. I mean, it's not the same clause that is found in the training data set. And this is done on random SAT problems. So what I'm showing you is that a very simple technique of time-dependent Gibbs sampling and lot of compute, of course, can actually give you basically solve constraint satisfaction problems. I haven't told the model that it is a SAT problem. I only gave it clauses and the true assignments. It figured out how to actually solve this problem. You can actually see that a lot of backtracking actually happens, right? I mean, as you can see, it tries a bunch of things and then it goes back and then it basically tries to figure out where all the clauses were wrong and then it tries to refit. I mean, there is more stuff about how AR models cannot do this, or it would be too expensive for you to do it, but it's very, very natural for diffusion to actually do. This is a layout generation. As you can again see, there's a lot of backtracking. That's why you need multiple rounds, because everything looks at what other decisions have been made and then does some denoising in an appropriate way, basically. And you can actually see how the layouts now look more reasonable. It's just that it's slow because I'm just doing multiple rounds of denoising, but in people in industry would like something very, very fast. But if you are a science person, then you will be happy with it as long as the quality is really good. We also have some results on molecule generation, but I don't have any like animation to show. So yes. No. So the backtracking is my interpretation of the of what happens here. It's just visual. All we do is the process that I told you. So we just add noise, multiple rounds. Okay, so the thing is, the trick is here. So I told you that you always don't noise. You actually leave things sometimes. So what can happen is that in the reverse process, if you look at the law will have a lot of mass of just leaving things as it is. So what can happen is that if you combine flipping versus leaving things as it is, and if you just look at multiple rounds of denoising, it will look like it can actually consider things to be as is, like leave them as it is, and then if some other change happens, then come back and then change it essentially. No, you could have made an error early, but then in the next round it will come back and visit it again, and it can actually flip it back, because I also allow multiple rounds. That's why you need multiple rounds. Yeah. Yes. Nothing is given, it's all data. Yes, everything is learned through a transformer model. All I have is sequences which I can noise, and I can reverse the chain using these conditional when I say conditional probability, it's not like analytically given. I'm just training something with a transformer model to just predict this at this point. No, this in everything that I showed you, we initialize with a random transformer and train only on this task. Yeah. Yeah, we can prove this. You can read the paper, it's proven. Yeah. I mean, the main thing is that I am not claiming Gibbs sampling is mixing in constant time. I'm just saying a time-dependent variant of Gibbs sampling, where the law is changing with respect to time, when coupled with the noising process like this, that basically mixes very fast. Okay? Yes? Yeah. Okay, so the thing is different boxes are different types of boxes, text boxes, figures, and so on. Whenever you write basically a full text box, or maybe let's say there's a figure, you would always follow it up with a caption. But the caption won't be on top of a text box. I mean, that's never how humans would write something like this. This doesn't know anything, so it first starts with a random bunch of boxes and places them in some arbitrary fashion. But then it knows from the distribution and then through the denoising process that it has to slowly place them like this. But it does a lot of backtracking. Right? Thanks.
So no more questions, then let's thank the speaker once again. And token appreciation. Filtering, image fusion, registration, compressed sensing, sensor network, localization, and optimization theory and algorithms. So several things. So yeah, so we're happy that Kunal accepted our invitation, and we're going to learn something from him today. Thanks, Kunal.
Yeah, thanks Parimal for the introduction. I think I'll have to put it somewhere. Okay, I'm unable to go back to the first slide. Strange. It's okay. I don't want to mess it up. So yeah, okay. Parimal, same problem. Yeah, I should take a tutorial on it. Okay. Yeah, thanks. So this is joint work with my student Devraj Banerjee, who is seated here. I was just joking that if there are tough questions, I'll pass it on to you. In particular, the questions about computation. So one disclaimer, there are not much results I'm going to show. There are only 25 minutes. So it's basically convey the idea of a paper that Devraj recently presented at ICML. And again, disclaimer that there isn't any at all. I mean, there's no distributor and there's no learning in this talk. Okay. So let me get started. So great thing optimization, there's no notational overhead. You can throw in the problem very fast, very first slide. So that's it. So you have an energy function and you have a domain. That's all, right? So the domain is hypercube. It's in fact, you can think of a string of vectors of length n, binary vectors, and the domain is the objective is a standard quadratic form. Simple. So now the catch is that had it been if the variable would live in Rn, then how do you solve this, right? It's not so easy to solve, but it kind of falls in this kind of eigenvalue kind of business, right? The tricky part is that Z is in 0, 1, and so these are called what are called quadratic binary optimization. It's self-explanatory. It's called also unconstrained because you can, there are problems where you have additional constraints. You have to put linear or other constraints, so you make a distinction. So the slides are, I don't wish to read to the slides. I've set it up so that you can read it like a paper. So the point, let me say that, is that there are two subtle points which are important. These are WLOG. So one is that we can assume Q to be, symmetric. This is a standard trick. You can symmetrize it. You can add Q transpose and just divide by half or something. So without loss of generality, the cost doesn't change. And the second thing is that if you choose a certain kind of representations which is not 0, 1 but minus 1, 1, then what happens is this nice trick that if you square these things, they're constant, right? Minus 1 square and 1 square, right? Unlike 0, 1. So what you can do is you can subtract off the diagonals. So without loss of generality in this spin setting, you can assume all the diagonals are 0. Okay. Because they don't matter, the diagonals don't matter. This is just a notation, this is a mathematical convenience. You'll somewhere calculate the Hessians, Hessians have the diagonal sitting on. Okay. The math should not change fundamentally, just that it's easier to do, let me say, and that's WLOG. You can just do that for any cubo problem. So there's a reason I'm talking about this spins is this Ising model, Ising model. Where this S is, it comes from, it has a physical interpretation. I'll come to that shortly, where S is a kind of a spin, and throughout this talk I'll use these jargons like spins, and I could talk about binary vectors, but I'll talk about spin configuration is just a vector, it's a setting of those spins, and I'll talk of E as an energy. The things which I'll talk about intuitively, it's easier to understand when I say energy goes down and things like that. Okay. So very quickly, let me run through the slides, not so interesting. So there are many problems, counting problems like graph cuts, I'll talk about max cut, partitioning, TSPs, etc. So you can model them as, so that's the best selling point actually. You don't want to sell it as a Ising problem. Usually Ising problem is not so interesting as a minimization problem. It's interesting as a phase transition problem. That's how it was invented, used. But so this would be the more modern, interesting application. Interesting is used for designing alloys and things like that. Pretty much all kinds of design problems where there is a coupling, right? There's a field kind of structure and someone sees the others, and then you have to come to an agreement or something like that. It's used in electronic design, wireless communications. Frankly, I don't know much about them. We have been mostly working on the Ising, and then we have tried it on number partitioning, graph cuts and things like that. Okay. So this is just a sales pitch, right, saying that this is interesting, but even if it's not, you will see something interesting comes up. So look at this max cut. This is a very, how do you say, this is a classical and very elegant way of counting actually cuts in a graph. This is the first step where you bring in analysis. You start from a discrete and try to move to the sort of analytic domain. How do you do that? A very simple observation that, just to go over that, what is a graph? There is a graph here. So those lines are the edges, and you set up a kind of a partition. It's a two-way partition, so you have zeros and ones, and you basically count edges which are crossing the, going across the partition. So for example, 4, 5 would not be counted, 1, 2 would not be counted, whereas 1, 5 and 3, 6 would be counted. So this, well, it's a counting problem. You just look at the graph, start counting, right? You first assign those labels 0, 1 and count. The interesting thing is that you can do that, you can do this counting encoding using a quadratic form. That's the core idea. Actually, if I'm correct, that it was Lovac who came up with this a long time back then. Gomez, Williams and others did that. So you can actually see the point is if these were equal, they would not count to 0. And only when the parity is different, they would count, right? So you're just basically counting using quadratic forms. That looks like a terrible idea, right? That looks like a terrible idea. Why? It's like using a, sort of bringing something more complex to count. The whole point is you can extrapolate, right? You can move from the hypercubes to the Rn or the thing, and then you start using calculus. That's the whole idea. That's what Gomez-Williamson did. So as I said, this starts counting a countage and it's 0. And just for the sake of terminology, this is a maximization problem, not a minimization problem, but there's a standard tick moving from maximum to minimum. You just look at the negative, so, and that brings you to the cubo problem. That's the reason I've put a minus. The minus is also because in physics that's the minus where try to minimize the energy, not maximize. Okay. So talking of the Ising model, so as I said, there's this kind of sort of systems with spins, up and down spins, and you want to have an assignment of spins which we can encode either using 0, 1 or -1, 1. And you basically, the data is that the couplings. Typically this is a constant and positive for at least the original ferromagnetic model. In spin classes you can have plus, minus and things like that. So you can have all kinds of things, but the point is that quadratic forms come up. Why do quadratic forms come up? Because you are trying to measure the interaction between SI, SJ through some weighting or coupling Jij, right? This is not so important. This is a kind of external field which is linear on the spins. That's the full model. But as I said, that minimizing, you see the minus coming up. So for example, if just quickly, if these were all positive, you see if all the S's were aligned, all plus or on minus, this quadratic form would be maximized and that would minimize the minus, right? So that's the reason why it's a energy minimization, not a maximum. So the problem is very simple, minimize E over all spin configurations, okay, which gives you this ground state. This is actually used in the physics just like that. They don't care so much about optimization. You get the ground state and you study its analyticity of something like the partition function with temperature. Okay, so so generally it's known to be NP hard cubo, right? So it's just a simple example is max cut is proven to be NP hard. The point is not so much that it's not that you don't do anything after that. So you want to come up with methods, approximation techniques. In fact, there are sort of zoo of techniques. I think this is how much, 30, 40, even more. I think all kinds of computer science people, physicists, everyone has contributed. There's like tons of techniques. I've not done a survey of them quickly. There's these two big classes. One is the annealing based or stochastic methods where you search. They're also called nowadays fancy called zeroth order optimization, where you just have the values and you just want to move around without looking at the gradients. Okay, yeah. Q, the matrix can be real values. Yeah, so that's I said it's a special case, right? So yeah. So there are special classes, right? You can use that for encoding and other things, but for real valued also, I think for Ising it's shown that it's hard, I think, for real values. Yeah, so that special classes are proven to be, but sort of. Yeah. So there are these two classes of techniques. They comes with their merits and demerits really. But the point is that we chose to take this route and realize that there is a problem. So the way people do, as I said, you start with the discrete problem and then you write it as a quadratic form and then you pretend that those are not 0, 1s and you are on Rn or let's say on a cube. So there are these convex and SDP relaxations. You can solve them using interior point solvers to arbitrary precision, things like that. They are actually at the boundary of hardness. They are incredibly hard to solve actually. You don't have a technology actually. I have a package which fails all the time. Okay, so these are not convex, some of them yes maybe, but SDPs generally is not very reliable, the current packages. So the point is that they are nice, mathematically they're very nice, they come up with guarantees, right? In fact, as you know, there is this famous result on MaxCut that there is this 87% guarantee, which is I think kind of something that cannot be beaten unless something is false. Okay. So the point is all that is nice, but you see these were done in the 90s, right? And people were happy. If you look at the papers, they were solving very small problems, which is fair enough. 90s, 10 cross 10, like 10 spins, right? I don't think so. 3 spins, 4 spins, right? Now you have 100 spins. In fact, Debraj has 10 to 8 spins. When you look at alloy model, you will have 10 to 8 spins. You look full physical model, you can't do that. So fair enough. So what's happened in between is that, you know, this deep learning and all that has come. See, what we understood the philosophy is that somehow miraculously gradient, all these first order methods work, right? No one knows why. There are kind of hand waving arguments, but they work. Simple. I mean, they fail also miraculously. See, in this case, it's not so much a problem if they fail, because you can measure energies. So you can restart always. You know, you have an assessment. There is no ground truth. You don't need a ground truth. You can measure the energy. If it's bad, or you take 10, you launch 10 iterations, look at the best and just keep that, right? But the point was that, can we also come up with some guarantees? Can we build systems which use first order, use gradients, derivatives, Hessians, things like that, and which are pretty much scalable, and also maybe come with some guarantees. Remember, these are hard problems. I'm not saying I can guarantee I can get the global minimum. It's a non-convex problem. So this was mostly our proposal is a continuous relaxation with the following guarantees we'll quickly go through. So every local minimum, you see, when you're solving on the local, when you're solving on the continuum, you stop at some point. There's nothing that tells you it has to be a binary vector, right? What you do is actually you round them, right? You get a fractional solution, you round it. That's a technique. You would actually have to do it in practice, because you will not get to the exact minimum, right? You'll start at a finite point. But I would say in theory, if you could get the exact solution, that would be a binary vector. We'll show that. That comes from design. It's not accident. And then we show that there is some kind of landscape. These are called landscape equivalences. We can show that the global minimum of the original problem, remember, it's a hypercube. Only some points have this least energy states, the ground states. We can actually preserve those ground states. We don't create new ones, right, which are called spurious ground states or spurious minimums, right? We'll show that. And then there's a nice characterization of the local minima of the continuous problem, right? So we have these local minimums. We'll show these are this well-known notion of one flip local minima. So there's this, all this I talked about annealing kind of techniques. Many of them go to a fixed point, and the fixed point is a one flip. That is, if you change one spin, your energy will not increase. That often, that's also a criteria, because you see, measuring one flip is very easy. It's order n, right? You run through all the flips, change one by one, measure the energy. If it doesn't go up, you're done. So we'll show that's exactly, I mean, it comes out of the design. It's exactly the same thing, right? So I'll not get into a lot of details, but I'll explain you the main idea. As a result, I cannot show you many images. Is that, see, there's this one standard trick that is done, is this homogenization. You can take an affine form here, sorry, a quadratic with this affine term and turn it into a pure quadratic, right? It's not so thing, but the point is it's you know, it's sort of now homogeneous. You can scale sigmas and all that, right? So henceforth we'll be looking only at this homogeneous model. I will skip Q. But S we'll use to remind you that those are vectors, binary vectors, and X would be the continuous vectors, right? So what do? I'll just throw some notations. Hn, we don't want to write this clumsy thing again. Hn is the Hamming cube, the hypercube, the discrete hypercube. S is a vertex of that cube, which we call a spin configuration. You can call it a spin vector if you want. And we assume, as I said, WLOG, this is it's symmetric and the diagonals are 0. So under all of what I say are under this setting, right? Plus I'll throw in some other conditions on the. So and then what do? We fill the cube. We move on to the continuum, and then we consider this energy function. So mind you that that's where the innovation comes in. So it has two parts. You can think of regularization. Simple. It's a penalty that we put in. The relaxed energy, let's call that has two parts, the standard term and the potential. Now see, this is the interesting thing, what Debraj did. So see, this, you don't want to make it very complex, right? This is what you have to deal with ultimately, right? So this has a high coupling between the x's. This we take to be separable, to just make life easy. You can still do things with that. So we just take it as a sum of, so basically you define a scalar potential and just throw it on all the coordinates and add them, right? It's a standard trick again. So that's how our separable potential is defined. Now this is the design problem. The design once you commit to that model, you can ask interesting questions, right? So can I choose a scalar potential phi? Remember, this is a scalar valued function, right? And consequently which induces this form such that the relaxed energy has the same local and global minima, right? It looks a little too much to ask for, but if I show you a picture, you will see it can be done actually. So it turns out there are three geometric properties that will throw in. One is symmetry, one is curvature, which would give a concavity, in fact strict concavity, and other is the boundary slope. If I show you a picture, you will see why those three properties matter up next. So we will abstractly show how these properties guarantee all these things. We will not commit to a specific form, but I'll convince you later that you can construct phis with having those properties. You can construct a family of them. But the point is that even when the landscape is preserved, these properties can strongly affect the practical. See, this is just I'm saying theory. In theory, it can do that and all that, right? So I'm not talking about algorithms first of all. This is not in the scope of this talk. But even if it does, it will hit a point. I mean, it depends on what kind of phi you take ultimately. So I should be able to parameterize this. So isn't that 10 minutes? Oh, I started early. Okay, so maybe I'll borrow 5 minutes. Okay. So from see, this picture actually tells you, as Debraj says, this is this should not be taken literally. This is not generated by a function. This was hallucinated. So it's a nice, it looks nice. It tells you what can happen, but this cannot happen for the function I have. So these are the hypercubes of these points. These are the minimums. You know, one of them would be the minimums. I think these are the minimums here. One flip, and then when you fill it in, you can start getting spurious minimums, right? So if you launch your algorithm, they'll go and hit that. So what you do is basically you turn the surface this way, right? You give it a negative curvature. So you push the points down to the corners, right? You know, you can't draw it that way. It actually say, Devin, this is not correct. If you look at the properties, it's also convex along lines. It cannot look flat like that, right? You can't draw. I mean, it's just kind of a rendering of a function. You just bend the function down. You force the minimums to go to the boundary, right? So that's where the negative curvature at the point comes in generally. So at least, for example, you don't want stationary points in the interior, right? So if you have strict negative curvature, that's ruled out classically, right? So that would be local maximums, right? You won't have local maximums at least. You can have saddle points. So I'll not get into details, but that's the intuition why I give the thing. So it turns out very quickly, the idea is that if you put evenness, just getting quickly to the point, it turns out that you change up to a constant. So it's equipotential basically. If you look at the grid points, it's equipotential. So all the values are equal. So what happens is, if you can guarantee that the minimizer, remember this is the relaxed problem, this is the continuum. So if the minimum, right, let's say global or local, whatever, you can force them to be on the hypercube, then it's automatically guaranteed that the minimizers would coincide, right? Because you see, you cannot go inside, right? You're forced to be on the boundary and you are equal with the original energy every time. So you're forced to be equal, right? There's a simple consequence of that fact. The whole catch is that how do you ensure this, right? How do I ensure that the minimizers of the original, the relaxed problem are at the vertices? Remember, they can be on the edges or on the faces, right? It's in high dimension, right? You might come down to the face or the edge. So the way you can do that is by having controls on that. So the point is that this concavity, we put in this concavity assumption on the potential, that should be strictly negative over -1, 1, right? So as a result, very quickly what happens is the curvature has two components, one coming original cost, the q, the original function, and then there is this curvature coming from the potential. Now that's the point, this vanishes by assumption, right? So as soon as you can control this to be, force this to be negative, you know that none of these points would be a local minimum, right? None of the stationary points would be a local, right? Because it goes down like this, you cannot have a point, right? So what happens because of this, the arguments are not very difficult, so I've just stated it informally. So a strictly convex function cannot have a local minimum at an interior point, not even at a face or edge, because you see it has a nice geometry, the faces are aligned with the coordinates, right? So remember, this is not a condition for E to be concave. I'm not saying that, mind you. I'm just saying that diagonals are negative. Why? Because I'll prove by contradiction, I'll use directions along the coordinates when I rule it out. I don't need to in fact, it's very hard to force this, right? You see there's a couple term queue and all that, right? So it turns out that the logic is that you can show that the local minimizers are on the hypercube if this holds. It's a simple argument. In particular, if phi is even, first property, second is concave, and if this difference is constant, it comes, your minimizers are exactly the same. Okay, so this is a simple conclusion that comes from the construction. But you know that those are all hypothetical points, right? You have not even written a piece of code, right, which solves that. You just have a construction, and on pen paper you can see all that. So the optimization challenge is not that we can magically solve the problem by relaxing it, right? Of course you can use all these fancy tools, Adam and all that, gradient math, things like that, heuristics and things. But the relaxed energy is generally non-convex, right? We can't hope to get, see, remember it's kind of concave, right? You build it to be that. So exact preservation of global minima does not make the problem easy to solve, right? That's not the point. You have to design an algorithm. So a practical first order method may at best return a stationary point. Actually not even a local. Getting a local is impossible almost. You have to have a theorem. Getting a stationary point is also very difficult. You have to prove it. It doesn't, it's like not like you run gradient descent, it will go to a mean, right? You need some control. So it turns out there's this KL function theory and all that. You can use that to show that it goes down to a local and all. So I'm not discussing all those points, but there's a very interesting question you can ask. You cannot avoid local minimums, but what are those really? How do they look like? Is it that the local would be close to some global or something like that? So I'll give a very quick thing. So the quick point is that I'll just come to the point. These are what I call the one flip local minimums. So the minimums which are, you know, when you define, you have a ball, right? So this ball is the Hamming ball. So you're just looking at points which are off by just one spin, right? That's not a global, because in a global 2 spins, you can change 2 spins and come down, right? So if you just look at one spin change, this is the optimum that you can. So that's the definition. Turns out, as we show in the paper, that there's exact equivalence between the two, right? So I'll just, I had sort of underestimated the time it takes to speak. I thought, yeah, so it's a better idea to putting more. Okay, so how long do I have? Okay, 5 minutes, I think it's good enough. I'll skip the results at that. Okay, so let me tell you what is the idea. So sorry, yeah, I'm very sorry. Yeah, so you see the whole art. So let's ask this simple question: what are these math based on? So we do some calculation. It turns out based on optimality conditions. Ultimately, everything is based. Actually, you don't work with the definitions, right? You have a condition which is more accessible. So let me tell you, there's a very interesting and intuitive condition of, I didn't know that, of one flip optimality. Right? The definition is uninteresting. It says that if you flip one, it doesn't change. You can't do. It turns out that it's a one flip if this quantity has a physical significance. QSI is the local field, like, you know, other guys impinging on you, right? That's QSI. It says that it has to be positive in sign. It has to match SI, the current spin that you have. If you understand, that's the idea behind many of these. I think this Gibbs sampling on this kind of algorithms, right? If there's a match, then you move on, right? And that has to hold for every spin site. Turns out this is simple. You just put it into the algebra and it comes out. Interestingly, there's a nice analog of that for local optimality, the continuum optimality, which apparently looks a bit strange with the signs reverse. I'll tell you why. So for this, we very well understand. We know what it means, right? In calculus, for optimality means if you move, it will increase, right? So you might wonder why there is a negative. It's because that if you move, if you're at a high, see, this is the point, you're on a hypercube. It's not for any point. If you're on a hypercube, if you move, you have to move in the opposite sign. If you're at 1, you have to move at a minus direction, right? So that's the reason this sign switches, right? So basically, this says that it increases, it's greater than equal to. So keep in mind that there's this nuance that, you know, have to be strictly, all the thing is there, right? For sufficiency, you have to be strictly, and necessary is less than equal to, right? So it turns out it's just you put this together and it comes out. I'll just probably get to tell you one thing which is, I think, important. I'm sorry, I think maybe the slides are there, you can have a look at this. I've totally underestimated the time it takes. to teach versus give a talk. So I'll just tell you one form, very simple, you can do it very simple, a quartic polynomial. You can take a quartic polynomial, 4th minus square. It turns out that, except this is a parameter, let me just tell you, it's written there, it's just something very intrinsic to your model, right? You just look at some min, max and all. So this is a model, forget that thing, but the point is that there's this balance between the 4th and square, so it turns out you can get both signs, plus side one thing and negative side one thing, right? And as I said, you can start parameterizing and all that, and you can ensure all those properties and all that. Okay, so yeah. So as I said, just let me show you one before I think this one slide to conclude. Let me just show you one equation which tells the whole story. This is the equation, as I said. So if you look at the gradient at a point, then it's, as I said, it's a negative of the local field. It's like going down plus your potential, right? So it's simple. You have to make sure this is positive or negative. That's all. So it turns out there is this condition which says that the slope, it should slope downwards. It should be negative, but not too negative. Okay, again there is a physical intuition to that. It can mask your points which were not local minimums, one flip. So you have points where it's going down, right, in the discrete counterpart. Now you bring in the continuum, and if it masks, if your potential masks that, it will start pretending like a local minimum. So that's the whole intuition behind the proof, and that's all. Okay, so I'll not get into details, just let me finish off with a discussion. This is a very important point. I've been hiding something here. So there is a gamma naught which it comes from the it itself is a solution of a minimization problem, which is as hard as the original problem almost. What you do is simple. You can, as you said correctly, q can be an integer sometimes. It turns out it's trivially 1, this constant, 1 or larger, because it's integer hitting integers, modulus you can't get zeros, right? So otherwise it's the LSB kind of thing. So if you have some delta times integers where a delta is your LSB kind of thing, it's at least delta. So you can estimate lower bound it quite easily. That's one point. I talked about parametric potentials. You can have a much larger class, and this is a very interesting point that we didn't discuss. It turns out we didn't talk about accuracies, right? We talked about the optimization problem. It turns out you can show an epsilon optimal relaxed solution is also epsilon optimal for the original problem, right? This can be shown. So what we are working on is designing algorithms which come up with provable guarantees. So in the paper we have used Adam and other things which seem to give good results. So we are just working on that. Yeah. Okay, with that I'll probably stop, and that's some results. Not, you can just look up the paper, and yeah. Okay. So thank you.
Time for questions. So in the SDP literature, there is a result at some point that says that the Cholesky decomposition of the optimal SDP solution can be at most root D.
Correct.
Right, and then there's this follow-up work where they said, oh, if I knew that the rank is only going to be root D, let me just describe in a Riemannian surface, you transpose U and all of that. And there people claim that if you just had not very adversarial Q, you can just do Riemannian gradient descent.
Yeah, actually that's a great.
So question is that going to be still slower? I mean, I just don't have a sense.
So Nicola Baumol, we used to sit in the same lab.
Yeah.
So while he was scoring, so he has an EPFL right now. So actually I'll tell you, it's like this. If it works, it's like magic, but it fails. It fails quite often. If you're looking at large scale problems, I'm not sure how well it would scale, but for medium size it beats SDP hands-on. SDP is very slow. That's good for teaching. I talk about that in my course, but when you use that, SDP is very slow. Yeah. Okay, thank you. Yeah, sorry. Yeah.
To Govin's paper, so where he takes he relaxes in higher dimension and then he has to project.
Correct.
But here you don't need to project, right?
No.
And do you go in higher dimensions?
No.
I see. Okay.
That's what we throw all that away. So it turns out that they tend to slow lifting, right? If
exactly.
If you lift plus, that's a killer mix. Lifting plus interior point methods.
Also, I haven't experimented with SDP, but so what is the wisdom to take away? Is that SDP is bad? It's slow?
No, it's just that it doesn't work on my machine. No, it's like it'll crash, it'll burn. No,
like for 100, like how, for what dimension?
No, you have 10 to the 8 atoms, physical model.
Okay.
That's good for doing math. So if you're a physics, then You can't.
Even the best solvers right
Yeah,
now.
no. See, I'll tell you something very strange. I was running CVX, sorry for the digression. I was running CVX for some other kind of project. Apparently, it was giving numbers which are too good to be true. And then there's this proprietary SDP solver. We wrote to them, they gave us a license. The numbers are very different and very bad actually. So it turned out we did a hand checking. We solved it by hand literally for a 2x2 problem. It turns out CVX gives wrong results. So it's not a technology. We just kind of, so LPs are, so if it's LP, it's very easy, but SDPs, I don't think you can trust
I
SDP
used to
solvers.
follow a little bit the literature on minimizing rank, nuclear
Yes,
norm,
yes.
and all this SDP. So all this is just for theory, not.
Well,
I see.
I won't make a statement. Okay, thank you.
Another round of applause for the speaker.
Our next speaker is Professor Nikhil Karamchandani. He will be speaking on small error cascaded group testing. Nikhil Karamchandani is an associate professor with the Department of Electrical Engineering, IIT Bombay. He received the PhD degree from the Department of Electrical Computer Engineering, University of California, San Diego. He was a postdoc scholar with the University of California at Los Angeles and the Information Theory and Application Center, University of California, San Diego. His research interests include information and coding theory, statistical learning, and inference and networks. Over to you, Professor. Please give a big round of applause for Professor Karamchandani.
Okay, yeah, thanks introduction, and also thanks for the invitation. So let's begin. I'm going to talk about variant of the group testing problem, which some of you might have heard of. So just to begin, the original group testing problem was dates back to the 1940s, and it was first studied by Robert Dorfman, and as a solution to this problem that was posed to him about detecting syphilis in soldiers who were returning from the World War. And the question that was posed, or the challenge that was posed, was, of course, you can kind of individually test each of these soldiers, but the scale of that is just humongous. Plus, most of these tests are going to be ineffective because most of them are going to be just negative, right? You're just trying to identify these. It's like a needle in a haystack type of problem. There are a few infected ones which you really want to identify. Most of the tests are in fact going to just be negative. So the key idea that he had was about pooling tests together. So you take samples from multiple soldiers together, you pool them and test these pooled samples. And the idea is that if you have a pool in which you get a negative result, then you immediately know that everyone involved in the pool is healthy. And if you have a positive test, then you know that at least one item or one sample in that test was a positive. So then you have to kind of identify which of those, right? And the key goal is now you have to design these pooling strategies so that the overall number of tests that you run is minimized. That is what the original group testing problem was for, and then he came up with some solutions, and then people built on top of that. So this disease testing was where group testing began from, but then it has found applications in all kinds of scenarios. So you can imagine any scenario where you have a large population, but the number of items of interest is small, right? And so in the original problem, it was you have a huge population of soldiers, but the ones you are interested in is this small set which are infected. But you can think of this in like a network tomography kind of scenario where you have a huge network with many edges. A few of them are broken. You're trying to identify those broken edges. Or in like a DNA testing type of problem where you have huge DNA strands, but there are a few kind of patterns that are of interest to you, and you're trying to identify those patterns from blood samples. So anywhere where you have a huge population set, but items of interest are few, group testing has found application in that. So if we want to set up this problem mathematically, you have n items, which is your population. You have some unknown subset of defectives of size at most k, and generally you are interested in a regime where this n is much larger than k. Each test is represented by a binary vector of length n. So, if I have a 1, that means that this particular item is included in that test. If I have a 0, that means that this particular item is not included in that test, right. And the outcome is of such a test is just a Boolean OR of these the status of these individuals. So, for example, it is going to be a positive if at least one of these defective items or these items is included in the test, and it is going to be 0 otherwise, right. So, in this particular case, there is this underlying defective item which is included in the test, and so we are going to get a positive test. If none of the two defectives were included in the test, then you will get a negative test, right. So, if I can now put together many such tests, and that is what is called a testing design, right. So, each such row of this matrix is a particular test, right. So, for example, this test gives you a positive, this particular test gives you a negative because none of the two underlying defective items were included in the test, and so on. So, you get many such tests, you run many such tests, and then you get a series of positives and negatives, and we say that such a testing design is feasible if by looking at the output vector you can then infer the underlying defective set. Okay, so, this is the inference problem you have. You have a bunch of essentially you run a bunch of tests, you get some binary outputs, and from that you have to infer the underlying defective set. And if you are able to do that for any such any possible defective set of size at most k, then we say that such a testing design is feasible, right. And our goal is, I give you the size of the population n, I give you the highest number of possible defectives k, you want to come up with testing designs which use the minimum number of tests possible, and furthermore you want explicit constructions, you want efficient decoding rules, and so on, right. So, that is the original group testing problem. So, for the past couple of years we have been looking at a variant of this problem which we call cascaded group testing, and the motivation for this one possible motivation comes from network tomography, which I mentioned is one application which people have used group testing for. So, again think of a network where you have a bunch of edges, and let us say there are two edges here which are perhaps congested, and I am trying to identify those two edges so that then I can resolve the issues there, right. One way to do that is you send these probe packets through the network. So, let us say you send a probe packet which goes from 1 to 2, comes to 3, and then when it is making this transition from 3 to 4, it gets stuck, right. Now, there are protocols where what will happen is that this 3 will then send back the probe packet to the source, and it will tell the source what link it got stuck at, right. So, now what you are getting is you are getting the this information that this probe packet went through a defective link, but you are getting something more. You are also getting the information about the first defective item that it encountered. So, there are many defective items in the test possibly, but you are getting the information of the first defective item that was encountered in the test, right. So, that this is giving you more information than what a binary probe would give you. So, similar kind of situation also arises in, let us say, recommendation systems. Think of the underlying population as possibly different topics that people might be interested in. You are trying to identify the 1 or 2 topics that a certain individual is most interested in. So, you again have every probe is like a list of topics that I recommend to you. You start going through the list from, let us say, top to bottom, and you click on the first link that is of interest to you. So, again this is not only telling me that the list had something of interest to you, it is also telling me the first item in the list that you clicked and that was of interest to you. So, again this is the kind of feedback that we are interested in. It also finds applications in online learning under the moniker cascading bandwidth. Okay. So, now if I want to model this kind of a setting and this kind of a feedback, again I have the same problem. I have n items, I have some unknown defective set of size k, but now my test, each test is an ordered sequence. So if I say the test 3157, I'm going to have this probe which goes from 3 to 1 to 5 and then possibly 7, but the feedback is going to be the first defective item that was encountered in this sequence. So in this particular sequence, the first defective item encountered is 5, and so that is what I received back. Similarly, if you run the test 1, 2, 3, 4, 5, 6, 2 is the first defective item that is encountered in the sequence, and so that is my feedback. And if there is a test where there is no defective item which is present, then I get a 0. That is the method. Okay. So this is our cascading feedback model, and my goal again is very similar. I want to design these tests, so I put together several different tests. I get the output corresponding to them, and I say that a testing design is feasible if this collection of ordered subsequences enables me to recover the defective set. Same goal, I want to now find given nk. Yeah.
Order is important because, I mean, I see in network it happens naturally.
Yeah.
But, so, I mean, 5 was defective even if I were to sample it first, right? Or no, or that order is important. You would only have discovered it.
So I would, yeah, so for example, if you look at this particular test, both, let's say 2 and 5 both, if they were defective, in this particular test all I will know is 2 was defective. I will not have information about what, because for example if you think about this network tomography type of example, if my packet is not able to cross the first link, first error is where I cross. I am not able to run the test any further, right. Similarly, if I give you a list, you click on the first link, I don't know whether you would have liked or you wouldn't. That is kind of there. Okay. So yeah, so our goal is very similar. What we want to now kind of compare, if we want to now compare this with the standard original group testing problem that I had mentioned before, right. So if I look at, if I had run the same kind of tests with the binary group testing kind of feedback, then all I would have gotten is yes and yes for these two, because there is indeed at least one defective present in this test, and no for maybe these two, and so on, right. So you always get more feedback in the type of, in the cascading group testing problem than you are getting in the vanilla group testing problem. Yeah. Yeah, so maybe let me come to that. So you can do adaptive testing in binary group testing also, and non-adaptive there also. Right now I haven't clarified about whether we are running these tests adaptively or not. Yeah.
Why pick a test which has only 4 variables?
Yeah, you can, so in general you can, if you don't have any other constraints, you can always run permutations. There is no reason to restrict to smaller tests. You might have constraints in terms of, for example, let's say if you think about the recommendation list, I can only give you 10 recommendations in a particular page because that is the size of the page. I cannot cover all the documents that are there or all the topics that are there. So there might be constraints that naturally kind of limit the size of the test that you can run, but right now I haven't put any such constraint. So if you right now if you want to think about it, you can just think about it as every test being just a permutation. Okay, so so a binary group testing problem or the kind of cascading problem always gives you at least as much information as the vanilla group testing problem. So any feasible design that people have come up with for binary group testing is going to be a feasible design under our scenario as well, right. So any upper bound that holds for binary group testing is also an upper bound for cascaded group testing. You will not require more tests than what is already available in BGT. The question is, how much does this additional information help you? That is the question that we were interested in.
If you take permutation, I think every row will be the same error, right? Because if you have
yeah. But so in so the position, the kind of which of these items was the defective one, that is the one that gives you additional information. Okay. Yeah. So there is no noise in the model, so you will never get a contradiction, right? I mean, if an item is defective and I encounter that item, I am going to always see it as a defective. It is just that you might see, it might be the case that multiple tests give you the same defective item as the output, because the items that were encountered before that item in this defective test were the same. That can always happen. So, for example, here the first test gives you item 5 as the defective, and the last test also gives you item 5 as the defective. But there is no contradiction as such here, because we do not have any noise in the system. If I see a defective, that item is indeed a defective. Yeah.
Is it not better to always have a permutation rather than having a smaller set, because having a 0 is not going to give us any additional, I mean, we are interested in identifying the defectives.
Yeah. So you are right. I mean, if there is no other,
Add to more number of tests.
if there is no other cost in the system or constraint in the system, then you should always do permutations. Yeah. So there might be other constraints that limit you from doing these permutations, but otherwise you can always do permutations. Okay. Okay. So to Amit Alok's question, right now, so there are two kind of branches in group testing. One is called adaptive testing, where you design these tests in sequence. You run the first test, you look at the output of that first test, then you design your second test. You look at the output of both of these tests, then you design your third test, and so on. So you are doing things sequentially. That is called adaptive testing. The other framework, which is non-adaptive testing, which we are going to focus on in this talk, is where you have to specify all the tests beforehand. So I don't get to see, I don't get to design my tests sequentially. You specify all your tests in one shot, and then you run them. The kind of the pro and cons are, of course, in adaptive testing you are designing your tests sequentially, so you have a better chance of designing good tests, so your kind of sample complexity will be smaller. But the benefit of non-adaptive testing is you can run all of these tests in parallel. You do not have to wait for the answers of the previous test to decide what your next test is. Okay, so both of these are of interest. We are going to talk about non-adaptive testing, so you have to specify all the tests in before the experiment begins, right. So now let's look at just a couple of examples to see where we might be able to gain in terms of cascaded group testing. So let's say there is just one defective item amongst these n items. How many tests will you need to identify this defective item in the cascaded setting? Just one test, right? It's so you just run any permutation, it will give you, it will identify the defective item for you, and there is only one defective item, so you are done. So you just require one test, right? What about if there were two defective items? How many tests then do you need then? Two tests, yeah. So one option is you run the forward permutation, you run the backward permutation. This will always recover any pair of defectives. You will get one of the defectives in one test and the other defective in the other test. So you require at most two tests. Right. So this, in fact, of course, is optimal for k equals 1 and 2. You require at least k tests to identify k defectives, and binary group testing would have required log n tests. Okay. This is something that is known for binary group testing. The optimal number of tests that you need for recovering k errors scales as k square log n. Right. So you would have required log n tests, something that scales with n. For at least k equals 1 and 2, the number of tests does not even scale with the underlying population. So there is clearly benefit that one can get out of it. Yeah, then you would require more. Yeah, so the obvious question is, what about larger k, and so we want to look at this kind of setting. Okay, so how do we come up with a feasible testing design? Like I said, a testing design is feasible if we can recover any possible defective set from it. Now what you require for that is that if you have two underlying defective sets which are possible, that then you should get different output vectors for them, right? That is what you require. So for example, let's say we have a situation where there are 7 items and mod k is 3, so there can be at most 3 defectives. This is my testing design. If I have the underlying defective set to be 1, 2, 3, this is what the outcome would look like. But if I have the defective set to just be 1 and 3, which means 2 is not a defective item, even then you can verify that the outcomes would have been the same, right, which means that in this particular case this is not a valid testing design, right. Now this, what we want is this kind of notion of what property does a testing design have to satisfy to be a feasible testing design. And if you kind of looked at binary group testing, this is going to be like a analog of what is called disjunctness for binary group. So here the condition is the following. So intuitively what I want is that if there is any defective set K, then I want every item in that defective set to have at least one test where it is the leader among the defectives, right. You don't want that particular item to get masked by the other defectives. If the other defectives come before it, then you will never know about the defectiveness of this particular item. So for every defective item, so this is essentially saying that mathematically, so for every defective item, I want at least one test where that item appears before every other defective item. That is the condition that I want, right. So in this particular case, we saw that if you have 1, 2, 3 as your defective items, you have a test where 1 is the leader among the defectives, you have a test where 3 is the leader among the defectives, but you don't have a test where 2 is the leader among the defectives. Okay, so this is not going to be a valid testing design. If I change this design to this particular form, then you can verify that for every possible 3 defective set, you always have one test at least where each of those items is a leader. That is the feasibility. And once you have such a feasible testing design, the reconstruction is very simple. You're just actually getting defective items as output. You just take the union of those. That is your defective set. Right. So we want to use, this is what we, so the work involves essentially using this notion of feasibility or this criteria of feasibility to design schemes as well as come up with lower bounds. Okay, so so yeah, right now I am assuming that we know K. If you don't know K, then also you can recover that. Okay. So there are 3 different criteria that people generally look at in the group testing problem. One is zero error, where you want to recover the defective set exactly always. The other is where you allow for you relax your recovery criteria a little bit. You allow some probability of error delta, and the last one is where I don't want to recover necessarily the entire defective set, but I want to recover at least a large enough subset of the defective set, some 1 minus alpha fraction. So in our first work, which was led by Vakar and was in conjunction with a colleague Niranjan of mine, what we looked at the zero error group testing problem. So this is a combinatorial problem. You have n items, k defectives. You want to identify exactly those k defectives. I want to essentially find sets of permutations which satisfy the feasibility condition, but the set size should be as small as possible. So the main thing that we found was the following. So if you have non-adaptive binary group testing, then essentially the number of tests that you require scales as k square log n. But if I give you cascaded feedback, then you get this exponential benefit. You go from log n to log n. Okay, so your number of tests reduces exponentially from this dependence of log n being the population size, to log n. Right? And the ideas were essentially combinatorial. We had to come up the lower bound was based on a result of Erdos on monotone subsequences, and the upper bound was based on this clever construction that Vakar came up with, which was an iterative construction. You build on the size of n to come up with the right scheme. So in maybe the few minutes that I have, I am just going to talk about the other 2 recovery conditions, which are small error recovery condition and the subset recovery. So this is a probabilistic framework now. You have an underlying defective set which is drawn from some prior, and I allow you, for example, in the small error case, I allow you some small probability of error. In the recovery case, subset recovery case, I am okay if you recover a subset of the defectives. So now the good thing is that the arguments become very, very probabilistic from combinatorial. So they are more elementary in that sense. So the first result that we have is that if you want to recover up with probability of error at most delta, you require k log k tests. and the scheme is very simple. You just take t uniform random permutations, and the decoder is just the union of the outcomes that you get, right. So now think of just random permutations. I want to identify these defective items, right. So now this problem just boils down to like a coupon collector problem. Every permutation is giving me one defective item as a set, and in fact because these are random permutations, one of those k defectives is going to be the leader in that random permutation. So it's like every time I run a test, I get one of these coupons uniformly at random. There are k underlying coupons, that immediately implies k log k tests, right. So this becomes very easy. You have an upper bound of k log k. The trivial lower bound is k, and yeah, we don't know how to kind of bridge this gap. Whether this dependence of log k is fundamental is something we don't know, but we have tried schemes which are, let's say, a little more complicated than just independent random permutations, but we still haven't been able to breach anything below log k. So this is something that we are unsure of, whether this is somewhere in between or whether it is k, and we haven't found a construction. Okay. Subset recovery is very similar. Now it's just that now I'm okay with recovering 1 minus alpha k, so it becomes a problem of, okay, is there a subset of the defectives of size alpha k that I never see, right. So again, that is an easy probabilistic calculation, and you can show that now you require k log 1 by alpha tests. Okay, so this is now just a constant, I mean it is just scaling linearly with k. If I had non-adaptive BGT, I would have again had something which looks like k log. So the number of tests required is just k log 1 by alpha. Okay, we've looked at some generalizations of this. One is allowing some limited adaptivity. If you do fully adaptive tests, then you can show that you can do it in just k tests. If you have non-adaptive, then we have seen require k log k. If I allow you m stages of adaptivity, then one can show that you get something that looks like k log kind of applied m times to k, and that the interest of time I'll skip the details. It kind of merges the idea of both subset recovery and exactitude. Okay, so yeah, I think I'll maybe close here. I had some results on bounded test size and also on estimating the value of k. If you don't need that, I'm happy to talk about those offline. Just to conclude, so we've kind of started looking at this new model of group testing, where we also get this cascaded kind of information about defectives beyond the binary group testing problem. We've looked at some kind of variants of the problem which have also been studied under binary group testing. There are a lot of interesting directions here. One, like I said, there are upper bounds and lower bounds that we have come up with, and there is often gap between the two. The second is, right now we have assumed completely noise-free feedback. Once you have noisy feedback or you have constraint testing like you will have, for example, in a network tomography kind of situation, then things become even more interesting. Yeah, okay. So yeah, with that I'll end.
Time for a few questions.
Yeah.
When the objects are noisy, how do these lower bounds get affected? Do the lower bounds stay same, or what kind of techniques do you use there?
No, this is yeah. I frankly haven't looked at that in detail, because it's not even clear how you. I mean, what is the right noise model is also not very clear here. Things can be very asymmetric in terms of whether you allow for false positives or only false negatives or both. So I think it's pretty much open. I don't quite. I think achievability is maybe easier in the sense you maybe do some sort of repetition, but yeah, lower bounds wise, I think things are still quite open.
So yeah, so if you're not allowed to do the entire permutation, right, and then you are sort of constrained to go like maximum subset. I mean, achievability is again easy, right? You can take a random subset of that size and
correct.
See the leader is in there, right?
Yeah,
but for that you must have achievability result already.
Yeah. So maybe let me just flash the result. So what we have is the following. So you pay if you are constrained to use subsets of size G, then you pay a penalty that looks like this. So this penalty, roughly speaking, is like kg by n. So what this is saying is that if you give me G, if the test size is of the order of n by k, that I can match what I get with unconstrained test size. If you go any below any below n by k, then you have to pay this penalty of n by g, and we have lower bounds that say that you will require at least n by g test even if you have cascaded feedback. So this n by k is like a threshold. Beyond that you don't require tests of size larger than n by k. Below that you will have a penalty that scales as n by g.
So thank you for that. I was thinking that would a good approach to make sure that each defective item or whatever you call it falls in a different bin, a different test set. And then I was thinking maybe using some Bloom filter kind of technique to make sure there's no collusion.
No collisions. Yeah. So I mean, so it's. I mean, if I think of just a general Bloom filter, this is going to kind of allow me to design tests which maybe don't have collisions with each other, which means they maybe don't appear often in the same subset. But here it's a little more than that, in the sense they might appear in the same subset, they might appear together. What you don't want is they appearing in the same order. So it is okay for tests to, the reason we get this kind of I haven't tried the Bloom filter directly, but I mean the ones that we are using are just like random permutations right now. I don't know how a Bloom filter would it give you the same kind of order. I haven't thought about it yet.
Okay, so if no questions, before I say thank the speaker, we have to go for the picture after this session is over. Okay, we'll go to the main building in front of that. Okay, now we can thank the speaker. So we'll go for the picture, but we'll come back at 11, right?
sensors are not playing, right? Yeah, that's what. It's not even detecting. That's the issue. Okay. So Salim's slides are so.
Srinivas, now you are eating into my diary.
Yeah. So sorry, sir. You beat him up.
Why did you not come here early?
All right, welcome back. Thank you for showing up for the second half of the workshop. Our next speaker is Chandamani Singh, Associate Professor in the Department of Electronic Systems Engineering. He received both his ME and PhD from here and has previously held research positions at INRIA and UIUC. His research focuses on communication networks, stochastic control and learning, and game theory. Today he'll speak on age-aware content fetching and broadcasting serving as a service system, sensing as a service system, sorry. So yeah, so this was the formal introduction. So two things. So Chandamani is a co-convener of the Center for Network Intelligence, and he's also a local MDP expert. So if you're stuck in any Markov decision process, he's the person to ask. I learned MDP working with him. So with that, welcome Chandamani.
Inside. Okay. It's okay now, right? Okay. Thanks, Parmal, for the generous introduction. So yeah, I'll talk about content fetching and broadcasting sensing as a service system. So to motivate the problem, let us see this picture. So we have a bunch of sensors on one side, various sensors sensing different modalities and applications. So applications need the values of all these sensors. The sensors values are dynamic, they get updated, and applications would like to have their most recent values as much as possible. And there is an entity in between. It's a cloud platform. We call it sensing as a service. We can also call it an aggregator. What this aggregator does, it collects the sensors values, it stores them, and then it can serve the applications. Okay, things will be. Okay. So it's kind of an intermediate entity. So applications do not talk directly to the sensors. They actually reach out to this aggregator whenever they, for whatever they want, right? For instance, an application can have an SLA with the aggregator saying that I want temperature value at any time, at any point of the time I should have temperature value that is not older than certain, there could be a constraint on the staleness of the value, and now it's aggregator job to ensure that it fetches the data from this temperature sensor and feeds to that network in a timely fashion. So this paradigm is called sensing as a service. Okay. So when I say who is the service provider, this fellow is the service provider. Okay. Now how does this SCSP, this is called Sensor Cloud Service Provider. So SCSP is the acronym for that. And what is the revenue model? How does it earn? So basically, as I said, the sensors talk to this SCSP for the applications talk to this SCSP for the values that they need, and they also have to pay this SCSP. On the other hand, SCSP, whenever it asks sensors for their data, it has to pay them. So its net revenue will be what it earns from the end users minus what it pays to the sensors, and this fellow will be interested in maximizing its net revenue, right? So this is the revenue model. Let me go into the details of formal details of our model, the model that we study here. So we consider a discrete time system. So these are the slot indices, right? And these bars, so I am focusing on a particular sensors, and these lines indicate the times at which sensors updates their values, right? So we can think of it like that. Sensor takes a sample at each slot boundary, but there are those boundaries where its values get updated. So, between from 1 to 2 the value remains same, at 2 you have same value as 1, but the value at 3 is different from the value at 1. So, a new sample is created here, right. So, this is the value update model at the sensor. As I said, users will talk to SCSP for whatever they need. SCSP will fetch data from the sensors, right, that is samples from the sensors, and then one assumption that we make in our model, though this is not necessarily the case in SCSP, is in sensing as a service paradigm. The assumption is that whenever this fellow sends something to one user, every user receives it. So, it is a broadcast model. So, even though the request may come from one user or from a subset of users, when SCSP serves that user, every other user updates its value, right. So, this leads to a simplification which says that, so everybody has the same sample of the sensor at any given moment, right. Okay. So, formalizing it even further. So, we assume that there is just one sensor and its values get updated according to a Bernoulli process, that is at each slot boundary a new value may come with probability p, and with probability 1 minus p the value remains unchanged. So, this is the sensor update model, and there are n users, each of those requests again according to Bernoulli process, and these request rates could differ. So, what I mean that user I at any slot will request for the sensor value with probability qi and will not request with probability 1 minus qi. Right. There is a fetching cost whenever SCSP asks a new sample from the sensor, it has to pay a fetching cost. On the other hand, if the users, say a user requests SCSP and SCSP has two options now. It can either fetch from the sensor and serve a new value, or it can just keep quiet, in which case we assume that it incurs an cost that is we call aging cost, and it depends on how stale the sensor value is at the requesting users, right. So, there is an aging cost. So, SCSP has to have a balance between these two costs. If it fetches too often, then it incurs a humongous fetching cost. On the other hand, if it keeps quiet and does not serve these users frequently, then it incurs aging cost, right. So, goal is to minimize the average cost. I mentioned aging cost. So, what is this aging cost? It depends on how old the version of the value here is at the time at which the request is made. To make it clear, let us see this picture. As I said, see these lines indicate the time epochs at which the sensor's value is updated. We define something called versionage of information. It is number of updates since the content is fetched and broadcast. So, basically say at this moment the user and sensor have the same value. So, versionage will be 0. When sensor makes an update, sensor samples an updated value, the versionage will increase by 1. Again at time 2 it will increase by 1 more. Here it does not change because the sampled value is same as before. A new version is sampled here, a new value is sampled. So, again the versionage increases. So, this is called versionage of information, and we assume that the VAOI cost is a convex function of the versionage. Okay. So, this is the model, this is the problem. Let me know if there is any question so far. Yeah. Well, it is not. So, the assumption is the values are discrete, and that is true in any, see if you take any system, there will hardly be continuous value. I mean the sensors themselves has finite resolution, right. So, they cannot sample continuous values, specifically if we talk of low power like low profile sensors. Okay. But there are other information of other notions of age, like something called age of incorrect information. So, those can capture some of those things. Here we assume that the values are discrete. Okay. Any other question? Sure. Yeah, so just to, so neither SCSP nor users know whether there has been an update at the sensor. So for this model, we assume that they know the rate at which updates happen. So on an, right, so from history, right, but if even if they don't know, they can learn, right, but we ignore that feature, that aspect, right. So they don't know when updates happen at the sensor, but they know the rate at that P parameter P is known to both SCS. I mean, it's known to SCSP that takes the calls. Okay. So again, to make things clearer, so we use VT to denote the versionage of information at time t, and SIT, as I said, the user's request according to Bernoulli process. So SIT is an indicator function that tells whether the user has requested at time t or not. Suppose there is no request at time t, then action of the SCSP is clear. It's just do not serve, because it doesn't incur any cost by not serving, right. So no cost is incurred. On the other hand, if their number of requests is greater than or equal to 1, there is at least one request, then it has two options. One is do not serve, in which case this is the aging cost that is incurred. SIT note, recall that it's indicator. If there is a request, there will be an aging cost, and CAIT VT, VT is the versionage of information, and this is a convex increasing function, right. Again, these functions could differ for different users because they may have signed different SLH, right. On the other hand, if it fetches and broadcast, right, then it incurs a fetching cost but no aging costs. Note that it doesn't have an option of broadcasting the value that it might have stored, because the assumption is that all the users also have the same value that it has, right. That's the broadcasting, that's the simplification that broadcast brings in, okay. And this is the average cost, long time average expected cost that SCSP would like to minimize. So again, there are two terms. This corresponds, AT is one, that is it fetches and broadcast and incurs a fetching cost. If it doesn't fetch it and broadcast, then this is the aging cost that is incurred, okay. So now clearly we have something called a Markov decision problem, where the state is basically, you could say SITs and AT can SITs and version is, they could be the VT, they could be state, actions are AT, and this is the single stage cost, okay. Well, so as I said, VT is not observable at SCSP, but we assume that SCSP knows P. So VT could be replaced by tau t. Basically, this cost could be written in terms of tau t. So in particular, if you see what is the expected value of VT at time t, it will be just P times tau t, where tau t is the time since the content is fetched and stored, right. So because the updates are Bernoulli, the mean number of updates in this time between tau t and t would be P tau t, okay. So now we can replace, in this MDP we can replace VT with tau t, and now we have a fully observable Markov decision process where this is the state space, right. So it's n plus 1 dimensional state space, okay. Now I'll talk about two scenarios. One is a homogeneous case, which is relatively easier to handle, and this is homogeneous in the sense users have identical request arrival rates and cost functions. Then the state can be represented compactly just by these two parameters. Tau t is the time since the content has been fetched and broadcast, and MT is number of requests. We don't need to distinguish between the users because they all have same stale version of the content, they have same request rate, and they also have same cost function, right. So we have this MDP, and the optimal policy turns out to be of threshold type. This wasn't difficult to show, but coming up with exact policy, it required some effort. So we have a we have an algorithm to compute this policy. So you see what this picture says, that if the number of requests is m, just see how stale the information is, right. And if it's beyond some threshold, if the staleness is beyond something, then fetch and broadcast, otherwise do not serve, keep quiet. And expectedly, if the number of requests is more, this tau bar m will be lower because the aging cost will be more, right. Okay. So we have an algorithm that gives this exact boundary very efficiently. It's actually O of n. If there are n users, it's O of n algorithm. it runs quite fast, we do not need value iteration or something. Okay. Now, the problem gets complicated when we go to heterogeneous case, because users now have different request arrival rate and cost functions. The state space indeed becomes n plus 1 dimensional, the problem remains same, right, but now it is very difficult to solve this. Actually, the algorithm that we have developed for homogeneous case can be applied there also. If we, so the idea is how much aging cost is for the users who have requested. Here it just depends on MT. Here, because aging cost could depend on, could be different for different users, we will have sort of 2 raised to n possible combinations of requesting users, and so those many distinct values of aging cost, and we can use the same algorithm that we had for the homogeneous case, but the complexity will also be like 2 raised to n, because rather than keeping track of the number of requests, we have to distinguish between all possible sets of requesting users. So, the complexity becomes humongous, right. So, this is where we propose something that seemed to work quite well in simulations, but we do not yet have a theoretical proof. Okay. But see, here is the idea. If we look at this optimization problem, we can rewrite it as follows. So, notice that here AT was the common fetching action for all of them. It was fetching action, right. If you fetch, you broadcast to all. We basically create copies of it. Instead of ATs, I am writing AITs, but all these AITs have to be same. It is not that I will fetch for one user and not for the other one, right. So, these two are equivalent problems. The other change that I have done here is, instead of writing CF, I am writing alpha I CF, where alpha i's are non-negative numbers that add up to 1. So, the point is that these two problems are essentially same. ATs, all these AITs basically they collapse to single AT because of this, and sum of alpha i's being 1, this last term becomes same as the previous one. Now, we say that instead of solving this n MDP, so these are like you have n MDPs, but they are coupled through a common action at each time. We ignore coupling. We ignore coupling and we just solve each of these individual problems, right. And now, if you see these individual problems, this is state space is just 2 dimensional, that is V for ith problem it is VIT and AIT. So, we are back to a problem that is as simple as homogeneous problem. So, this is the single okay. So, this is what we do, solve per user problem, right, just 2 dimensional state space. But what we do is we also introduce additional fictitious fetching cost lambda I. So, there was, note that this fetching cost was already there, we bring in additional cost lambda I, and we will see how do we use it, and we solve this MDP. Now, it is quite clear that for this problem, if your version age is beyond some threshold, you would fetch and serve that user, otherwise you will keep quiet. And what that threshold will be, that will be function of lambda I. If lambda I is more, that threshold will also be higher, because you are incurring more cost for fetching, right. So, what we do is we determine so we basically flip the problem. We ask, rather than asking for given lambda I what should be the minimum age so that you fetch and serve, we say that given the given the staleness, what should be the maximum value, minimum value of lambda I for which the optimal action is do not fetch. Note that if lambda I is more, you will not be willing to fetch, right. So, what is the minimum value of lambda I for given tau I, so that the optimal action is not to fetch, and this is something what is called Whittle index in multi-arm bandit literature, though our uses of Whittle index is quite different here, and I will comment on this point a little later. Okay. So, we solve this problem, and it turns out that for determine minimum lambda I, and that we call Wi tau I, for which the optimal action in state tau I is do not fetch. Now, what about the original problem? What would you do in the original problem? So, this lambda is sort of telling us how much value is in fetching and serving that particular user. What we do for the original problem is just add up all these indices, right. This tells the collective value in fetching and serving all the users, right, and that is our heuristic. This is the collective value, right, and if it exceeds minus okay. So, if it exceeds minus CF, sorry, okay. So, then fetch and broadcast. So, CF is the cost that you would anyway incur for fetch. So, I think this should be there should not be a negative sign here, right. So, this is the collective value in fetching and broadcasting. This is CF that you cost you incur for fetching and broadcasting. If this value increases the cost, then you fetch and broadcast, else do not fetch. So, this is our heuristic. Now, I said that the indices are called Whittle indices. Now, how our usage is different? Sure. Okay. So, in restless multi-arm bandits, this is the restless multi-arm bandit problem, where you have to pull, where there are multiple arms, you have to pull one at a time. What you do is you again compute this Whittle indices and you pull the arm for which the index is maximum, for which the problem was little different, right. But again we use the same Whittle indices, but and now we are using this indices in it slightly differently to make a decision of taking this common action for everyone. Okay. So, after that there are few numerical results. I will skip those. I will just show one. Well, this is exactly what I just said now. This is our algorithm. So, this algorithm, so basically for homogeneous case, because we had an algorithm to compute the optimal policy, we compared the optimal policy with our heuristic, and they seem to be quite close, and suboptimality gap basically indeed diminishes as the number of arms, number of users increase. For heterogeneous case also we had similar algorithm. Now, just this last slide on while we have not been able to see, note that standard results for asymptotic optimality of Whittle indices do not work, because our usage is different, right. We are right, it is not a restless multi-arm bandit problem, but we were wondering why these do well, and we made a few observations here. I will just point to this. So, this is my last slide. So, if we increase, so to see why these work well, we increase number of users, and in the at the same time we also increase fetching cost, like linearly with number of users, right. And the Whittle index based policy turns out to be of this form. See, M is number of users that request at any slot. G tau is a constant that depends on the staleness of the constant. It turns out that if mg tau is greater than Cf, the policy suggests you fetch, otherwise you keep quiet, right. So, this is same as this, where Cf, okay, I divide by n on both the sides. Note that this M is binomial, or it is I mean it is a random that depends on the parameters Qi, right. As we take n to infinity, this M by n, this basically converges to, so basically this each of this M is sum of indicators that are Bernoulli, right. So, law of large number kicks in, and we have a deterministic rule now, right. If n is large, then it turns out that with probability 1, the Whittle index policy will become periodic, right. And then we were wondering if the optimal policy also shows that behavior, and it turns out that that is indeed the case. So, here this is the optimal policy's variance of interfetching time as per the optimal policy, and it looks like that variance indeed goes down. So, that is optimal policy also becomes periodic, more and more periodic as number of users increase. Though this is something that we have not been able to prove, but this sort of tells why the two policies do the same thing, right. Here is another intuition why the two do the same thing. So, these are tau bar m, that is threshold on staleness, basically fetching threshold on staleness. Why the values for a smaller value, and m is the number of requests. So, while the value, this threshold for a smaller values of m are little different, beyond certain m the two thresholds are same. So, one threshold corresponds to Whittle index based policy, and the other one is for the optimal policy. Beyond some m the two thresholds collapse, they coincide. So, this tells that if the number of users is more, with a high probability, most often you will see more than, I mean a very high number of users, right. Almost every time you will see very high number of users, and the two having same threshold, the two will basically fetch or take the same action. So, basically the two will fetch periodically at this with the same period, right. So, we do have a few intuitions why this policy does well, though we do not have any proof. So, this, as I said, still work in progress. So, just to summarize, we had basically novel uses of Whittle index policy to to address the so-called curse of dimensionality in MDP. And though I am dealing with a very specific problem, I think in spirit similar problems arise in many contexts, where there are multiple well, stakeholders, and you have to take an action that would affect all of those. Okay, so I'll stop here. Thanks.
Time for a few questions. Can I invite Amitabh to start setting up?
Thank you.
Let's thank the speaker.
Up. This much that.
Next speaker is from IIT KGP. He is assistant professor in Department of Electronics and Electrical Communication Engineering at IIT KGP. He obtained masters and PhD both from IIT Bombay and has previously worked at Cisco, and he was also a postdoc at Chinese University of Hong Kong. His interests include information theory, communication security, distributed signal processing, and decision making. Over to you.
Thank you. Yeah, thanks firstly for having me here. It's a nice occasion to meet all of you. So this is joint work with a BTech student, Arya Chaudhary, and it was recently presented at AMAS. Okay, so the context for this is basically the Caesarean tale about deception, and the specific twist that I'm going to bring in here is the fact that apart from deception, an innate object of that entire experience was the strategic timing involved. Okay, so the focus of this talk will be on strategic timing and how it can lead to something called Bayesian deception. The nomenclature Bayesian deception comes from its connection to a very classic microeconomics problem. So this area is rooted in inference as well as more microeconomic theory. That problem was called Bayesian persuasion. So I'll lead up to it in a bit. I'll spend a bit more time on the problem setting here, so my result presentation will be a bit skewed. I think it will take less time, so please bear with me. Okay, so let's go to this motivating scenario. So the scenario comes from financial markets. So you have Harry, who's basically carrying a distressed asset. So imagine he's a hedge fund, and what happens here is that there is an asset failure, which is known to Harry. Okay, the asset failure is random. So I'm going to denote it by capital lambda, and we'll always imagine that the time evolution is discrete to keep things simple. And what happens here is, and this is my figure that I'm going to overload as time goes. This is the market, which is basically calm, snoozing here, but it's calm. And when market goes in panic, you have this, and asset failure. The moment the market decides, comes to know about it, can lead to market panic. Okay. Now here is the other party involved, which is the rating agency. I'll call her Alice, and later we'll have another person pop up there. But the rating agency is basically tracking Harry's asset quality, okay, and it's independent. Now here the point is that the rating agency will be the proxy for the entire market to pick up the failure of the asset, the signal, right? So this becomes a very important point of failure, or the detection of the point of failure. So you want the rating agency to figure out the failure time soon. So that is what we are going to call this blue box, the market detection time. Okay, so the gap is a problem here. Now let's try to understand the game involved. So there are two parties. So let's look at it from the hedge fund owner, right? So his basic goal, being a selfish party, is to delay the awareness of this failure. And this is what he has now. So the rating agency crucially depends on the signals revealed by Harry. So in that case, he can have some sort of control, and this control, as you will see, will be partial. So he can make signals available to Alice, which will perhaps make it harder for her to figure out that failure. Now here is the important point. So, and this will reveal an important inference problem that is hiding underneath here. Some of you may have already figured it out, but essentially think about the asset failure. So the asset failure in a time series can be essentially seen as a point which differentiates two different quality of data signals. Okay, and some of you have seen this, would immediately recognize this as a change point detection problem. So this problem is sort of sitting on top of a classic inference problem called the change point detection problem. and Alice here is basically trying to figure out that change point as quickly as possible. Now what happens here is, depending on the signal, and this is what Harry can control, he can control the signal before and after the change point, and that signal will essentially be the one which he will try to make as similar as possible to delay. And you can show sometimes that the difference, the KL divergence between the two distributions before and after the change point often are inversely proportional to the detection time or the stopping time. So here is the game now. So Harry basically selfishly, so this is important, he's selfish because he would have some sort of a goal, and we'll actually add on to this goal a bit later. Choose the pre and the post change distribution, so these will be firmly in his control. What we need is these distributions to be over the same simplex. That's a restriction we'll put in this problem. And we'll also need them to be feasible. For example, we don't want to allow these cases where the distributions are exactly the same. That obviously will be impossible for any meaningful rating agency to figure out, right? So we can't have a P equal to Q. P and Q will be my proxies for the distributions before and after change. Okay, so the point here is, if you think about this entire exercise from Harry's point of view, this is basically a problem sitting in this area of microeconomics called strategic information design. Okay, so another way to see this problem is I'm going to present to you a problem on strategic information design, where Harry, the sender, has this particular goal. He can control the pre and the post change distribution. And this is how I'll denote the asset failure and the pre and the post change. But I have not told you everything about the problem. There is another part to it. Okay, now think about it from Alice's side. Let's see what are her goals involved. So of course, as we know, we would like to detect the change and immediately issue a downgrade, right? That is the goal. Now here is the point. So this is, we would like to reduce this gap. That makes sense from Alice's perspective, because if she delays that, then there is regulatory action that may follow her delay. So she's supposed to be doing that job as a rating agency. The other problem is the following. This is also something she should be mindful of. She should not be anticipatory putting out signals before the asset failure has come through, because that can cause market panic. So if the change has not happened and she puts out a signal, so there should be a penalty, more like a false detection sort of goal seen in the context of change point. So in that sense, early detection will cause market panic, and then the asset failure is almost inconsequential because the costs are humongous given the market panic caused. So the question for Alice is, should she depend only on Harris's data passively, or can she actively sort of also participate? And the point is, she now brings in this active probing mechanism through another party which is co-located at the rating agency, and let's separate out that auditor as Elizabeth. So what is Elizabeth going to do here? Both are part of the rating agency, but she's going to be basically putting out questions or queries to Bob, and Bob will be expected to give responses along those lines. Okay, this is basically to filter out a lot of control that Bob has in the problem right now. And this is how it will happen. So it will be a sequence of queries that will be sent, and Harry's responses will be according to those questions. And the hope is that with this active interaction, the detection becomes faster and hopefully correct. Okay. So think about it this way. So given the probe, what I'm going to have is now this sort of a dictionary of the pre and the post change distributions. And what will happen in this problem is, we will force Harry to essentially declare this dictionary beforehand, and then given the probe, he will have to honestly play those particular distributions. Okay. So in some sense, the dictionary means a collection of PQ, and every PQ pair is some sort of a pre-change, post-change pair which has been publicly declared. Okay, and just to make it relevant, because if I, for example, as Elizabeth, discover that there is a particular signal which is extremely discriminative, there will be a cost associated with it, because more informative signals should ideally, or in principle, make Alice pay more, right? So that is also something that's going to come in. So these are all the different aspects of the problem. Just to summarize, the goal design here is to basically get a good sequence of probes, and at the end arrive at a quick detection of the change point. So that's where the sequential change point problem comes in. And of course, for Harry now, the sender, this is the important part that comes from typical assumptions in classical microeconomics. He has to declare his signaling dictionary, that PQ pair, ex ante. In the sense, he has to declare it advance and stick to that. It's a bit like a code where he reveals PQ and then sticks to that choice for different probing signals. And of course, both of them you'll now see will have this selfish part. So this is where the problem differs from a classic change point problem, because now we have the sender also as a selfish party. So there are two different parties involved here, and we would like to formalize this interaction. And here our motivation comes from a very classic work on Bayesian persuasion. We'll come to that a bit later. So how does this differ from prior art? So firstly, because of the interactive nature, we call it the interactive deception game, and the Bayesian deception framing comes from its genesis from Bayesian persuasion. The key point is there is an information asymmetry. Crucially, Harry will know the lambda, the change point, but the rating agency, in this case Alice and Elizabeth, will only know the distribution attached to it. So that's where the information asymmetry is. And there are two layers of endogeneity, because the stopping time crucially depends on the data generated by Alice, but by Harry, but Harry's own data is crucially coupled to the feedback probing that has been done by the rating agency. So there's a two-layer of endogeneity involved here. Okay. And given the nature, given the fact that Harry plays first, or at least has a control on how the detection time varies, this can be seen as a leader-follower problem, where unlike say a classic persuasion problem, there's a mismatch utility here between the sender and the receiver. Okay, so this problem, as I had said before, sits at the heart of three different areas. The first one is obviously optimal stopping in the context of quickest change point detection. Now here are some important references along the way. It's a very niche and very big field actually, but almost everything in sequential analysis is attributed to the foundational work of Abraham Wald. But specifically there was a sequence of works by Page and several others actually, Lorden and others. The problem that the reference that is closest to this work, and I encourage this, it's a nice reference actually, it's a book by Shiraev, who has a lot of work in this line, and our treatment almost follows from his treatment on this book on optimal stopping. Okay, it's a nice book. The second part is, this is actually what is called an active sensing problem in sequential inference, and active sensing itself is again in a very active area, particularly starting from the work of Hermann Chernoff, where he first proposed this problem of sequential design, where the designer had active control on the kind of data that was being shared with the designer. And subsequently, of course, there are now different lines of work, particularly in what is called the sequential hypothesis testing problem. One particular work that we benefited from was the active sequential hypothesis testing, which was by Nakshwar and Zavidi, because they have a very nice interpretation of sequential hypothesis testing and its connections to various problems like feedback communication. Okay, that insight definitely helped us here. Finally, our treatment is almost exclusively inspired by this work which appeared, so the work by Kamenika and Skenskov in Bayesian persuasion. So this is a work that appeared in American Economic Review, and it has followed a significant line of work on signaling theory, and particularly strategic information design, starting from a very important work called job market signaling. And this particular strategic information transmission can be seen as the original genesis of the information design problem, when the goals are strategic. Okay. So while all of this is true, our inspiration, as I said, will be, the nature of the results will be crucially borrowing the language from Bayesian persuasion, and that's why there will be certain other ideas I'll be talking about in the nature of what is it that we are seeking here. So the main question, maybe I can pose that question. So the main question we are going to address here is, doing all the other analysis, is when is there benefit for a sender in terms of deception? Can I deceive the receiver or not? Firstly, we have to crystallize what that means. And then having crystallized what that question is, we would like to know when is there a benefit of even indulging in a signaling game to accrue this benefit of deception. Okay. So formally, I'm already 10 minutes plus into the talk, so let me now formally quickly give you the setting, because there are some choices that are important. So again, the lambda is our change point, and we'll always assume that it's on a discrete geometric random variable. For certain reasons, we assume this to be a zero modified geometric, which means the change could happen even before the first data point has happened. Okay. So if q was 0, this would be a classic geometric random variable. The second thing is, we have this signaling scheme, as I said. So the sender, which I'm going to also call sometimes the principal, it's a principal agent problem, is going to have a dictionary which we are going to basically address as collection P1 Q1 up till Pn Qn. And what is the n here? The n is basically the alphabet. The 1 to n is the alphabet that is allowed for the feedback probing. And the important thing is, this is ex ante in the sense, once the sender fixes the signaling scheme, in the run that subsequently follows, he is not allowed to revisit the PQ allocations. Okay, he has to declare this and follow it. That is the standard premise on any information design game. And it's, of course, once it's fixed, it's known to all. But our goal will be to find the optimal choice of such a signaling scheme. So that question we still do address. Sorry, P and sorry. Oh, T is the stopping time. I'll come to that. That is the time where I'm going to stop. Yeah. Okay, so there's going to be a probing signal from the agent. So that's how the problem starts, the first probing signal, and that will trigger this conditional kernel. The kernel depends on, as you can see, so signal will be ST at time t, and that will conditionally depend on the change point as well as the current probing signal. So just to illustrate what this would mean, so if I have an asset failure at lambda, and forget the time for now, the stopping time, what's going to happen is if the first probing signal, let's take it, the probing signal will take values between 1 to n. So let's say the first probing signal is 2, that would mean that the agent would be constrained to pick a distribution PQ, and crucially then it will check, it's conditioned on lambda. So if the t is less than lambda, which is the case here, it will be basically putting out S1 according to the pre-change distribution P2. Okay. Similarly, if you have F2, then again I'll check it. If it's F2n, so it will forcibly pick up the Pn Qn and then pick my S2 according to Pn, because that is a pre-change distribution corresponding to time 2. And this will go on, and if there is a 7 which is post-change, you will see that now the S7 will be sampled according to Q1. Okay, this is how a change point problem goes through. And the goal here is now addressing the question Karthik had. So t is basically going to be my variable for stopping time. So in this case, as an agent, given a pi and the lambda, the agent would try to find a stopping time. So this is a random stopping time, classically defined, and of course there's a intermediate set of controls, and the goal is to have a stop as quickly as possible, as an agent would do, and hopefully correctly. So this is how the three parties are, but remember that the two parties here, the decision maker and the prober, are essentially the same rating agency. Okay, I'm just artificially sort of split them up. So okay, this is already clarified, so I take the pre-change post-change distribution. So the agent strategy is basically a pair t comma ft, which is the t where the t is the stopping time, it's a ft stopping time here, and the f, the sequence f1 to ft is the sequence of controls that I have up till the stopping time t. So what I have is now a generic agent utility function. So I will always denote the agent, remember is the receiving party. I will identify the utility for the agent with the letter small u. So it will depend on the two things, which are the actual change point and the detected change point, which I am currently calling a lambda hat, and there is a sequence of probes which can typically go as long as they can, right? Now I'll of course make an assumption here that the specific utility that we have, we will not allow general utility cost functions, but we will allow a utility function of the following kind, and this comes from the motivation we had. It will essentially have the false alarm cost. Did I stop too early? And that will incur a cost of C1. Second is, did I stop too late? That would incur a delay cost. And to capture the probing cost, I will essentially have some function C of f, which can be, for example, a C of f can be, so every probe f has a particular cost structure attached to it, and that is known beforehand. So this is going to be my utility, which is in some sense the negative of the cost for Alice. And the agent problem is obviously, I'm sort of writing it in terms of a maximizing of the utility, but you can think of it as a minimizing of a average cost. So the goal here is basically to figure out a del bar, which will be maximizing this expected utility. Okay? And of course, you can think of it as the minimization of the other side. Let's think of it from the sender's side. So here, again coming from the way microeconomics typically views these problems, I allow a general utility function, and this time I'll call it V instead of U. The important part here is the utility for the principal will depend on the actual change point and the stopping time. So I'm now not allowing a lambda hat, I'm just calling t as my lambda hat, and there's no probing involved. So the cost now is some utility function which takes me from the set of lambda comma t to r. Okay. And in that sense, the principal's optimization problem is to find the pi star, which will essentially maximize its utility. Now here is the thing you have to note. This is a coupled optimization problem, because crucially the agent gets to decide the signal, and in some sense induces a particular stopping time and a feedback sequence of probes. And in that sense, this problem, and this is how this area is spawned, the goal is to essentially move this entire seemingly complicated optimization problem into a problem exclusively at the sender. So we want to essentially try to attempt to write this optimization problem and the entire coupled optimization problem as a single problem at the sender. And the important object for us here will be the beliefs, because if you think about it, the action of the receiver, since the optimization problem is null, if we are able to show that the action of the receiver is completely belief dependent, then the signaling scheme that the sender has essentially controls that belief, and in some sense the sender can run that exact same problem at its end. So choice of the signaling scheme is the choice of inducing a convenient posterior at the receiver, and that's why this problem is firmly in the realm of Bayesian setting. Okay. So the prior is this geometric QP. So there's a I'm sorry. So the posterior and the so prior is my geometric. This is a prior that is known to both parties, and the goal of this entire exercise to induce a particular posterior on the change point at the receiver, and the signaling scheme essentially allows me to do that. And given the fact that all this information is public, the distribution, the sender essentially can control this particular posterior. So let's try to see if we can move this entirely on the sender side. So here is the goal of this problem. The goal is, if we have this entire interaction, we would like to sequentially follow this line. First, okay, forget the pi star here. The first thing we would like to know is, given a particular signaling scheme pi, we would like to know how does an optimal receiver work, which is how does it pick its optimal probes and how does it stop. That's an optimization problem we first like to understand. So that would be the optimal sequence of probes and optimal stopping rule. Note that this will be done for a particular pi. If we are able to solve that problem for a particular pi, we would like to discover a pi star, which would then correspondingly allow us to get this delta star of pi star. And if that happens, if it's solved precisely, then we'll essentially discover the Stackelberg equilibrium for this game. Because if the sender is operating at pi star, the receiver will act according to del star of pi star, and there will be no reason for the sender to deviate from that. Okay, so that is the goal of this exercise. But as you'll see along the way, my goal is also to figure out this question of benefit of deception. Is there even value for a sender to engage in deception? Because there may be some problems where after doing all of this, there may be no conceivable meaningful utility that the sender gets out of it. Okay, in that case, and I'll give a picture. This again now ties in with the previous work on Bayesian persuasion. So this is the part I'll just go through a bit quickly. So firstly, let us look at the receiver side problem. Given a fixed pi, what do we do? And this is classically borrowing from change point, although in this case we were looking at an active change point problem. So we had to solve a few things separately. So what is the sequence? The typical approach here is to first figure out the feedback control, and as is known in this area, the classic approach is to do the Bellman principle. Okay. So what we do is, we are looking at the optimal signal at time t, and it can be shown that that optimal signal will be some function f of the posterior at the immediately previous time t minus 1. So mu is my posterior. Now what is the specific posterior that is tracked here? Now here, this posterior in general is a posterior on the change point conditioned on the filtration at up till time t. But what is shown, okay, I should have put that here, 1 second. Okay, I'm sorry, I have that expression somewhere, I didn't put it here unfortunately. So here is where we borrow from Shirayev's classic work, where he shows that there is a specific posterior which allows you to write a very natural Markov process. Because if you have a nice Markov process, you can hope to do a very nice Bellman analysis of it. And that is the posterior which we use, and that posterior is shown to be the conditional CDF on the change point. Okay, that statistic allows you to write a very clean Markov process. Okay, so I'll skip this part. So this is basically the Bellman principle, where what we end up doing is we look at the immediate cost and the cost of continuation, and we would essentially, if I sort of break up the two parts, forget the expression. So the main principle is, oh, okay, I do have it here. Okay, so the main point is I would try to figure out the cost at every time. I'll figure out the cost of immediately stopping or continuing. And whenever, so the boundary is what I need to figure out. What is the boundary which tells me whether I should be continuing or not? And here is where that statistic plays a role. So that statistic is Shirayev's statistic. So let me give a figure from a different problem altogether. This is stuff that some of you may have seen. So if I look at the bad figure, so excuse me for that. Essentially what I have is the x-axis, which is telling me time, and the y-axis is some statistic. In this case I have plotted the LLR, the log likelihood ratio. That's not the statistic in this problem. But what happens is, essentially, if we are able to solve the problem of Bellman, we'll get this curve, which is basically the curve that separates the stopping region from the continuation region. And what we are interested in is, if I look at this first curve, it is the first time this curve, the log likelihood, instantaneous log likelihood, hits that particular threshold. That is the time I stop. So a similar sort of figure emanates for the Shirayev statistic here. Yeah, this is the statistic I was talking about. And the important part is, unlike the classic Shirayev work, I've skipped a lot of details. The stopping time can be written in a very simple form. It's a single-sided test, which is nice, that we are also able to show. But unlike Shirayev's work, this statistic, the threshold ends up depending on the full posterior. So that is a criticism of our result, but it looks like, given the active nature of the probing, we cannot avoid that, at least at this stage. Okay. Yeah, I'll maybe skip this part. Yeah, so this is a big takeaway. The test retains the signal. Stopping time has a test which is single-sided, which is nice, but it depends on the entire posterior. And our interpretation of that, we mentioned this in the paper, is that there is a interpretation where the varying nature of the boundary essentially comes from the fact that information has a price. Okay. So let me skip this part. the other part is from the sender side, and what we end up doing is, I'll skip a few things, but the important part is to show the reduction that at the end the stopping time is just a function of the terminal posterior. This needs a bit of work, and here what we are able to do is we are able to write the statistic at the sender to be a new function capital V hat, which exclusively depends on the posterior only, the stopping posterior. It doesn't depend on the actions and the change and the detection of it. So that's the important reduction. And given all of that, now here I'm sort of going through, let me use this figure. So here is the final takeaway picture. And this is a simplification of what really happens. So if I think of the belief on the x-axis, okay, this is the belief that the receiver has. An important point on the belief is the prior. So mu naught is a prior on this belief space. Okay? And what we're able to do is, because of the reduction, the sender's problem of utility can be written as, the utility that the sender gets can be written as a single dimensional sort of a function which depends entirely on the posterior. That looks like this blue curve. So what is the big takeaway in this? So the big takeaway is there is a hidden concavification principle that can be discovered in this problem. So these are principles that are important in game theory, where we can sort of use the concavification principle to comment about the benefit that one can accrue through such signaling games. So in this case what happens is we are able to show that there is a minimum concave function that majorizes, that's the red curve, and the entire story of is there deception or not can be picked up from this particular. So this is the big story. So if this red curve has a necessary gap from the blue curve at the mu naught point, at the resting posterior prior, and if this gap is non-trivial, then it tells us that there is a signaling scheme the sender can pick up which will give him a benefit of persuasion. On the other hand, if this curve, the blue curve, is already locally concave at mu naught, then there is no majorization that will benefit, I mean, will give us a benefit, and hence, even though it can go around trying to find the signaling schemes, there is no benefit of deception that it can accrue. Benefit of deception is, given the prior and given the posterior, what does the value the sender get out of it? Okay, so that's basically the Stackelberg equilibrium, and this is basically a summary of all the things that we do. We figure out for a particular pi what is the stopping time, and we are essentially able to figure out the Stackelberg equilibrium. And under that equilibrium, we are able to say whether there is any benefit in this entire exercise of deception. I should clarify a few things. So some of the things that I've hidden here, because it takes a bit of time to prove those, is in dynamic static, so if you have a finite horizon problem where there is no random stopping, then these, the stopping does, showing that the utility depends only on the terminal posterior is something that is not very hard. Again, the not very hard is to be qualified. The issue here is in a random stopping time problem, often the stopping posterior is not enough to complete, it's not enough to completely characterize the T star, and technically the sender should know the T star and the stopping posterior together as the full state to sort of simplify its utility. But in this particular setting with the geometric random variable, and that's where Shirab's work is important for us, we are able to show that not the full state T star and mu at the T star, but just the mu star is sufficient for us to complete the problem. But this problem has a lot of issues. There are illustration difficulties, because unlike the classic SHT problem, the change point has a very large alphabet. So even making these pictures or giving nice illustrations becomes a bit hard. That's the work that's ongoing. But let me close out with this part. Thank you very much.
Time for questions. If there are no questions, let's thanks Mikalo. Yeah. There is one.
The next speaker.
Okay. Thanks.
Yeah, thank you.
Yeah.
Oh, thanks. You can come here. Thanks. Thank you. Thanks a lot.
Okay, I'll take it. Next is Sandeep. So this workshop has 3 organizers. Chandramani is the co-convener of CNI and also co-PI in this project. And the other one is Professor Ruaiher from Rutgers University. He is associate professor in the Department of EC at Rutgers. His research focuses on information theoretic security and privacy, coding theory, distributed and federated learning, and decentralized algorithm. His work has been recognized with several prestigious honors, including the NSF Career Award and the Google Faculty Research Award. So today we'll present random walk learning and the Pac-Man attack. So please join me in welcoming Professor Salim Ruwaya.
Thank you.
So while he's setting up, maybe like I know Salim since he was a first-year graduate student at Texas A&M. We overlapped quite a bit. In fact, my years in PhD was a subset of, his years in subset was a subset of my years at A&M. And he was a TA for me for information theory, and he would unnecessarily cut marks. I don't know if you remember, but you can have a rebuttal.
Oh, so I don't need a mic. No. So thank you, Parimal, for inviting me, and I have no recollection that you were in that class. So not first. The slides first. Yeah. Can I do this?
If you want to go to videos.
I will ask your help.
Okay.
And how can I move slides? This?
Yes.
Okay.
No, I think the first slide is the little bit issue.
Okay. I'll figure it out.
Yeah.
So thank you, everyone. What I want to talk about today is a problem that we started thinking about maybe a year ago, me, Parimal, and also my student and postdoc. And I'll probably have more open questions than answers. And one of the reasons that I'm here is that to solicit more Parimal time and help to be able to finish solving part of this problem. So again, you see Parimal here. Shingran is my postdoc. He's now in Singapore. He got a faculty position. Zonghong got poached by JP Morgan, so he's graduating soon. And Rohit is an undergrad. He's done most of the simulations, and Hari Haran helped a lot with the videos that I'm going to show you. So let me start directly by the problem. The problem is a decentralized learning problem, but actually that is just the motivation. So the actual problem that I want to talk about is not really about the learning. Actually, the essence of it is not about learning, but the motivation comes from learning. So what I have a network. The network here is a completed graph, but it doesn't have to be a completed graph or fully connected. It can be any network. And I have nodes. Each node has data, his own personal data. And what you want to do is that you want to train a model collectively on all the data in the network, on the data on all the nodes, but you don't have a central server. So this is very similar to federated learning if you know about, but there is no central server, there's no cloud where all these nodes can send the gradients to the central server to do the aggregation. So there is no aggregation, no central server. So the only thing you can do is that each node can talk to its neighbors. So that's the only thing we are allowed, that each node can talk to its neighbors. And by each node talking to its neighbors, you want to somehow perform this decentralized and distributed computation and get a performance as much as possible as if all the data was in one place and you were training this data, the model on this data. Okay, so I want to kind of emulate the data being in one place and being trained on by a central server by just having these decentralized spread out nodes talk to each other. So I'm going to assume a very, very decentralized setup where every node just knows the existence of its neighbors. He does not even know he belongs to a big network. He just knows that I'm connected to these guys and that's it. And I can talk to these guys. That's everything that a node knows. So the model here, it's just a standard machine learning problem. I'm doing empirical risk minimization. This is the local loss function at each node. And I want to try to minimize the global loss function. So for many people of you who've done control or optimization or distributed optimization, the first thing that comes to one's mind is consensus or gossip, meaning the setup that I have here, which I won't be talking about. I want to talk about this setup. But in consensus or gossip, what happens that it's usually in every, not only, I think of it not even in political science. If you want to run a country with no leader, so you have two options. Either everyone is a leader, and this is consensus, or everyone gets to be a leader for a short time and then passes the leadership to someone else. Okay? So this is the gossip or consensus where everyone is a leader. This has been studied a lot in the literature. The way it works is that it's true that you're trying to train a model on all the data in the network, but what happens is that each node has his own model, and he updates it by talking to his neighbors, right? So at each point in time, if you have n nodes, you're going to have n models. You have n models, each model associated with a node, and each model is updated based on the local data and the messages that I get from my neighbors. So each one train on local data and send the output to his neighbors. And then you use your neighbors' messages to update your model based on what you receive and your local data. And you keep doing this, and you can show that actually all these models are going to converge to one model. That's the consensus. And this model is basically what you would have obtained if you trained the model on the data in one place. Of course, the question there is that how fast this conversion is going to happen, this consensus is going to happen. And of course, it's going to depend on the graph topology and stuff like this. And this is very well understood and very well studied. What I want to look at today is more a different kind of algorithm, which is based on random walk. So in random walk, instead of having n models, I just have a single model in the network, right? So I start from a random place in the network. So here, let's say I pick this node. He initializes the model with x0, whatever it is, and then trains on its local data using SGD or gradient descent, whatever first order method if you want, or whatever method you want. Once you update based on your local data, because this is the only data you have. So you train as if nothing exists in the world except your data. Then you choose randomly one of your neighbors, and you passes the data to that neighbor. You passes the model to that neighbor. Okay? So I'm assuming you choose uniformly among your neighbors. You could do whatever transition probability matrix you want. But what I'm interested in is how this is going to evolve. So once you transmit your model to your neighbor, then the neighbor does the same thing. He takes, instead of starting from a random model, x0, now he has a better estimate. So he starts from the model x1, and then does a gradient descent on his own local data, and then so on and so forth. And this keeps going through the network in a random walk fashion. And actually, you can show also that if you do this, then you converge to the global model, right? And I want to study this case because I'm interested in learning on this model with lower communication costs. So if you can see here, you have n models, and you have all the edges being activated. So in terms of trying to push for consensus, it's going to be much more, the communication cost is going to be much more higher to achieve consensus. Whereas here, every single bit you spend is going to go on updating a single model. So it's much more efficient in terms of communication and computation. Of course, there are also advantages here, because here actually this is what this talk is about. Here, even if one node leaves the network, it doesn't matter. This whole thing keeps going. You don't even need to know that one node left the network. Whereas here, if the guy that is holding the model right now dies, everything is lost. And this is what I want to focus on. So basically the communication and computation advantage that you get from random walk is coming at the expense of some, I would say, vulnerability or fault tolerance and actually security issues that I want to talk about. Yes? Yes. Yeah, because this is, I'm assuming this network is doing something else other than, So this, you can imagine this is running in the background, or these nodes are collecting data, doing stuff, and you want the model to be kept being updated. Any other questions? So this is basically the random walk gradient descent. Basically, at each step, you pick a node, one of your neighbors, and you send the model does a gradient descent, and so on and so forth. What I want to focus on is this security attack that I call the Pac-Man node. So you assume that some nodes in the network are malicious. Here I have one node, and I call it Pac-Man because the way it acts is that once the random walk visits that node, he's going to eat the random walk, meaning the random walk will stop progressing. And if this guy asks him, oh, did you get my model? He say everything is okay. So he pretends that everything is okay. He sends all the right acknowledgement messages. He does everything so to fool you so you cannot know that he actually has stopped the random walk. And you can see the effect of this can be very disastrous, because once the random walk hits that node, then the whole distributed computation task is gonna stop. So, and like I said, so I assume that this is stealthy behavior, meaning it's not like a fault. It's not like the node is temporarily unavailable or the node died or I don't know, something bad happened if this is a wireless channel, because then you can detect it with some acknowledgement. So this is more like an active malicious adversary, a Byzantine adversary that can try to fool you.
Is that pacman allowed to also send some other update?
So what? So far, so that's a very good question. So let me figure out this thing. Yeah. So what he does, the only attack we consider now is that he can decide whether to kill it or let it pass with a certain probability. We haven't looked at that he can add errors or send wrong models, because we just want to understand that first. I'm going backward. So you can say, what is the big deal? Instead of having one random walk, let's feed the pacman, start with 10 or 20 random walks and wait. Of course, you could do this, but depending on the graph, how big is the graph is, and how long is your training or training task, this may be not a good solution. It'd be too much of an overkill. Here I have, for the same graph, I mean, you can think of it. If the graph is connected, eventually you're going to hit the pacman and die. So this is an irregular graph, and I start with 10 versus 6 versus 5 versus 2 random walk, and then this shows you how long these random walks are going to live on average, because eventually everything is going to die because the graph is connected and all the random walks are going to hit the bad nodes and are going to get eaten. So basically, if you use many random walk, which is not a very bad idea, what's going to happen is that you're just delaying the inevitable. You're not solving the problem, right? You're just throwing resources at the problem without solving the problem. What is missing here is that it's true that you included redundancy at the beginning, but you need a way, a mechanism to kind of regenerate this redundancy, replenish this redundancy with time as the pacman is causing damage in the random walk by making them terminate. So in order to replenish the redundancy, so if I start with 10 random walk, I want to make sure that if the number of random walk goes down maybe to 5 or 4, you want somehow a mechanism to create a new random walk. So I'm going to look at this framework that we call CDT framework, where a random walk can duplicate. So a random walk can decide at some point under some local rule. By the way, if there was a central server, this problem wouldn't be a problem, because you can just, these random walk can ping the central server, and if the central server does not hear a ping, he knows that something bad has happened and I can take some action. So there is no central server here. So, and these random walk don't see each other. Okay. So what we need a rule for each random walk to make a decision, either to duplicate, like in here, or a node to just to start a new random walk. This is the create. Or maybe if you have somehow you overreacted, you created many random walk, and this is too much, causing too much overhead in the system. Maybe you want to terminate some random walk on purpose. So these are the actions that we have. And the whole question that I want to talk about today is that how can we have these rules, the create, terminate, and duplicate, in order to make sure that at any point in time I have a controlled number of random walk in the system, because I don't want the number of random walk to blow up, because this is too much, it will be taking up too much resources. I mean, ideally I just need one random walk. And also want to make sure that I don't have extinction. So I'll make sure that the number of random walk does not go to 0, or if it goes to 0 with very low probability. Okay? So all I wanted to is that design these rules to guarantee these two properties. Oh, these two properties, and there's the third property is that I want to make sure, yes?
So if there is no attack, is there still any reason to generate multiple random walks?
No. At least under this setting, no. No, under this setting, no. Maybe if you want faster mixing, You would generate many random walks, but that's it. You do whatever you do and you leave it. You start with 10 and leave. They're gonna remain 10. Yes. It's not clear how we can do it. Right, because it depends also how much information you want to carry. Of course, you can say in every random walk should carry a, I don't know, a book of every node it has visited, but this is way too much memory. So I'm losing, it's kind of cheating because the whole philosophy of this is to have everything decentralized. You can keep a log of everything, like crazy, what is it called? The chain, what is it called? The blockchain? They have this, whatever they call it, they keep everything everywhere. I don't want to do that. So I have two solutions, and I don't know how much time I will have, but I will try to explain some of these two solutions, and then we'll wrap up. The first solution is what we call duplicate a flate, and the other one is create a flate, and that's what I want to do next. So the duplicate a flate, the algorithm is the following. I'll try to explain it in high level. So basically what happens is that every node has a clock, and it keeps a clock about when it was the last time it was visited by any random walk. So when a random walk visits me, I reset the clock. And if I know that in normal times, if there was no bad node, I should be visited maybe every 10 seconds or every 20 seconds, right? So I know if there's nothing bad has happened. But then, so that's why when the clock goes above a certain threshold and I haven't seen anything, meaning no random walk has visited me, I assume something bad has happened. And then the next time a random walk goes through me, I'm going to create a duplication. That's the whole thing the algorithm does. And it satisfies what I want in terms of decentralization. I'm only basing this on my local information. I have no clue what's happening in the rest of the graph. All I have is my local timing information, and based on that, I'm creating the duplication. Can I have help with the videos? So I have a video for you. So. Do you want video, or you have big O analysis of the algorithm and the correctness proof? And only you. Let me see. I want the fast extinction, it's called. Parimal, you'll never get your points back from information theories. Is that the fast extinction? Can I see the full title? I want to make sure I play the right movie for you guys. No, but then, yeah, I'll play this for now. I'll figure it out as I go. Okay, so let me explain the setup. So my graph here, I've shown you like complete the graph, but here it's on a grid, meaning it's a grid. Maybe you cannot see it here. Now, instead of having one Pac-Man node, I have, I think, 10. These are the red nodes, meaning every random walk that is going to go through the red node is going to die. And the duplication rule meaning is 10, meaning every 10 seconds or 10 steps, if a random walk does not visit me, it means this is a red flag, and the next time a random walk visits me, I'm going to duplicate. That's the rule. Now let me see how many, yeah. Let's play a video a little bit and then I comment. So I started with one random walk, and then after 10 seconds it duplicates. And here, what I'm doing here, I'm keeping track with time how many random walk I have in the system. They know themselves? They don't know. No one knows the location. No one knows the location. Yes, they are. Yeah. No. So you can see here that because the threshold 10 apparently is a little bit too relaxed, then you're kind of oscillating over a low value, and I'm going to speed up a little bit. I don't know if you die here. Actually, you don't. I mean, so far you don't die. But you can see you're almost dying, but eventually you're going to die. You can see here what's going to happen to the number of random walks. So it just starts oscillating. Now, if you're a little bit if you're faint-hearted and then you're afraid that you're gonna die, because this is the video where actually what happens is that is the same setup, but you start, it's a different simulation, different randomness. And here you can see that, I guess that's what I wanted to show you originally, is that here you can see what's going to happen is that the number of random walk, like you go back to 1 and eventually that guy dies and it's gone in this simulation. Okay? It's repeating. So how can I forbid this from happening? I could play with the threshold. Instead of waiting till 10 steps to duplicate, I can make the threshold shorter, and this is what I want to play next if I figure out which one it is. Threshold delay. Maybe this is, oh, threshold 3, yeah. So I went from threshold being 10 to 3, meaning every 3 steps, if nothing happens, I'm going to duplicate.
So you duplicate when you see the next.
Yeah, yeah.
So what if you change that, right?
Meaning?
Once the threshold passes, I will duplicate with whatever value, the model that I had last.
That's a very good idea. That's what I'm going to do next. This is the next algorithm. Yeah. So here I'm duplicating too fast. So what do you think is going to happen here if I'm duplicating too fast. So number of random walk is going to keep increasing. The question is, what's going to happen after a while? Is it going to keep increasing or is it going to settle? And why? What do you think is going to happen? Why? Yes, exactly, yes. So there is somehow an inner, a hidden feedback loop in a decentralized way. The more, it's true, like you can think of this as a birth rate process, but the birth rate and the death rate are not fixed. And you're not controlling them. The more random walk you create, the more, like you said, the more random walks are going to go through the node, resetting the clocks, the less you're going to create. So there's a very interesting inherent feedback loop that's going to regulate the creation process. And this is exactly what's going to happen. So I'm going to fast forward to you, and you can see that it kind of settles. There's always a probability of dying. That's not going to go anywhere. Because there's always a probability that each one of these nodes is going to walk to if the graph is connected. There's always a non-zero probability each random walk is going to walk to its death. That's always there. But now we're going to really delay that happening. Meaning, you mean the death? Yeah, it may not happen. I don't know. I haven't thought about infinite. My brain is very finite. I'm thinking finite. Because I know Parimal in the paper, he always adds, maybe you want to comment, because you always add a finite graph. Do you have any comments, Parimal? So can I go back to the talk? Oh, by the way, I have the videos, and actually we have a website where you can choose the graph, you can choose this threshold, and then see the behavior. What do I have here? So here I plotted the number of random walks with time, which is the graph you saw in the videos, for different graph topologies. So I have here ring, I think this is complete graph, a random regular graph, and then Erdős-Rényi graph. You always see the same kind of behavior, which is if the threshold is too low, meaning you're not replicating fast enough, you're going to eventually die. The number is going to go to 0. It's too high, yes. And then if it's above a certain threshold, then you're going to oscillate around a certain value. I have 5 more minutes. So 2 takeaway message. Let me remember, what are the 2 takeaway message? Oh, boundedness. First, you can show actually it doesn't go to infinity. So this is kind of the self-regulating. You can just compute the drift and prove that actually you're bounded and you converge. The proof is in the paper. The other takeaway message is that there is a phase transition. If the threshold is too big, then you're going to die. And then there is a threshold below which there is a positive probability of surviving. And this is still kind of a conjecture. We're still working on proving it. I'm hoping me being here, we can get something. In the paper we just presented at ISA, we proved that this phase transition exists for for a different process that is close to it, but I'm personally not very happy with that result. So I want to prove phase transition for this process. The phase transition is in the following. If the threshold is too high, you're going to die. If it's too low, there's a big probability of surviving. If for those of you who know branching processes where you have individual that have offspring in an IID way, then you can show that this phase transition exists as long as on average you have at least one offspring. So if on average you have a little bit above one offspring, you survive. And if it's less, then you're going to extinct. But this whole analysis does not apply for us, because for us everything is interconnected. You have a state in the problem. It depends where your random walk are at each instant, and also there's this kind of, it's not independent, right? At each step it's not independent. It depends on the number of random walks. So just lifting the results from branching processes literature is not going to work. Am I going backward? Maybe. So this is the conjecture about phase transition that I'm hoping we can prove it. The other one is create iflate, is that we want to avoid extinction. So what's going to happen is the following. Let me see if I have a graph. I don't have. I have a video, but there is no time. So what's going to happen is the following. Instead of every node is going to keep the latest model when the random walk went through that node, like you said. And then if the clock surpasses a certain threshold, he doesn't care what's happening. He's going to start a new random walk. But instead of that random walk starting from scratch, he's going to start from the latest model he has. Maybe this is not the most updated model, but it's better than starting from zero. Because you don't want to keep starting from zero, because then you don't make any progress. What does this avoid is that there's no extinction. So if you simulate this, again, you have the number of random walk here, and you have steps. You can see that although and the threshold is very big. I mean, 350 doesn't have a meaning, except you have to know the graph. But in this case, it's too big, so you're gonna die eventually. But then you die, and you go extinct for intermittent amount of time, and then after a certain amount of time, some node is gonna wake up and think and realize it has been too long since anyone has visited me, and I'd better start my own random walk, right? So I think, how much time do I have? 2 minutes. So you can prove, again, the same kind of results using Lyapunov drift analysis, that the number of random walks is going to explode to infinity. You can also get, in this case, you can get actually some bounds on how large is the limit. So actually in the duplicate iflate, we show that it converges, but we don't have an idea about the order of magnitude. Here you can have a better analysis. And actually, if you create with a certain probability Q that depends on the number of nodes, which is also a little bit iffy, because I assume that every node does not know anything. But if you assume that nodes at least have an idea of the number of nodes in the graph, and if you create a new random walk with probability that is big O of 1 over n squared, then you can guarantee that roughly the number of random walks is going to remain constant irrespective of how big the graph is. So you can have much better control on the number of random walk in the graph. This is kind of the regime where you create with the probability 1 over n squared. N is the number of nodes in the graph if the clock is above a certain threshold. Now let me get to the final thing. What happens to the convergence of the algorithm? So far I'm just talking about number of random walk, but what's going on to the model that's being updated? If you look at the end, or whatever, if you look at the graph at now, most probably there's no random walk that has survived so far. But what has survived is that some child of a certain random walk. So what you can do, you can trace back the child to the parents, parents, and that sequence of random walks form itself a random walk, but it's different than the law governing this new random walk is different than the original random walk. Why? Because this fake random walk never visited this guy, the bad node. So the model is being updated by a surrogate, a fictitious random walk with the skewed transition probability. In that sense, you can prove that the model is going to converge, but to a little bit a biased model, because it's going to avoid the bad nodes, and actually it's going to avoid the neighborhood. So there's more probability that is skewed towards away from the neighborhood of the bad nodes. just because you condition on the fact that you survived. That's the whole thing. And you can bound how far you are from the actual model. So the actual model X star is as if there was no Pac-Man versus what the model I'm actually learning. This is pretty standard, so it's nothing fancy, but we want just to quantify how far is the bias. And we run some simulations. This is maybe, you can see here so I'm running here creative plate on MNIST, or I don't remember which one it is, but I think what I want to highlight is that you can see here if the threshold is high, then you have this kind of staircase kind of behavior. What's happening here is that in these times, plateau times, what's happening is that there is no random walk in the network. So you have a period of extinction, and then suddenly one node will wake up and start computing. So in some sense, everything survives, but with a delay. Now, if you decrease the threshold, you survive, like here in the blue, but there's it's not clear in this picture because here you have a lot of random walk in the graph, so there's a big overhead in terms of communications. So I'll conclude here. Thank you.
We have time for one or two quick questions. Yeah.
So this is exactly what I showed at the end. So there is, it misses it, but it doesn't start from scratch. You agree? It starts from the latest model he has. So the model is a bit stale. Oh, this will happen only at the beginning. This will happen a little bit at the beginning, but after a while, everything will mix. Yes. I mean, of course, it's going to depend on the well, let me ask maybe a different question. How can I pick these thresholds, right? Yeah. So we're, of course, it depends on some connectivity property. I mean, I assume some spectrum property also. We're looking at I would love to have some self-adjusting threshold, something like TCP/IP, that it just learns and then adapts, but we're working on this, yeah. I mean, at the beginning when we started working on this, I just wanted something that does not grow with n, with the number of nodes. I just want a number of random walk that does not grow exponentially. That's what I want.
No further questions.
Thank you.
Thank you.
Thank you. Do I get a gift? I hope it's edible. I mean, not an edible, but.
Our next speaker, last but not the least, Professor Sandeep. So Sandeep is an associate professor at this very department, ECE. He obtained masters and PhD and worked as a postdoc at TU Delft. Right. And his interests lie in signal processing and machine learning applied to graphs and wireless communication. Today he will talk about decentralized constant learning. Over to you, Sandeep.
Okay, thank you. Thanks for having me here, and thanks for the invitation. So thanks also to, for Salim to set up the stage. So what I'll be doing is talking on the right setting, that is the gossip and the consensus, not on the random walks. But more specifically, I'll be talking something about constraint learning. So it's a decentralized optimization problem where we have constraints that we have to satisfy, and I'll focus on two challenges. Depending on how time permits, I'll go through that sequentially. One is heterogeneity in the data. That means that we have different clients in the distributed setting, and the data is not IID, it is heterogeneous. And the second challenge is about privacy, so maintaining privacy in the context of differential privacy. So I'll go through that as we progress. Most of the work, I mean, all the work is done by Robin, who is sitting there. So he'll be in a better position to answer questions, tough ones, and the details related to experiments and other things. Okay, so Salim already gave you a bit of context about decentralized learning, but since Robin made these nice pictures, I will go through them anyway. So old school centralized learning, you have many different clients, edge clients. They gather local data sets, and then what you do is you transport data to a central server, and then the central server runs this machine learning model or a deep learning model that you want to basically obtain. Now, of course, there's a central point of failure. There is a cost associated with transporting data to the central server, and also there is a privacy concern there. Okay. Now, in the decentralized setting, there are two different paradigms. One is the federated learning setting. The other one is the decentralized, which I will focus on. In the federated learning setting, you don't transport the data, but what you do is you basically leverage the computational capabilities of these local clients. They train some local models. And these local models are then shipped to the central server, which performs some kind of an averaging or a consensus. And then you basically broadcast back these global models to these local clients. Okay, so then this goes on and on till you basically are happy with the models that you have. Naturally, there is a communication overhead because there is a communication that's happening back and forth between the clients and the server. And also, there is again a central point of failure, right? So what happens if the server fails? How do we proceed? The other paradigm of doing this decentralized learning is the following, where you have an underlying communication network or a communication topology. Each of these clients, as before, have their local data sets. They train their local models, but then they only talk to their neighbors. Okay? So they talk to their neighbors, exchange model or gradients, and then they arrive at a consensus, right? So again, depending on the type of the communication network, which is modeled as through a W matrix here, we can basically show convergence, right? So depending on what type of problem we are looking at. So what we have here is two challenges that I already mentioned. One is, as before, as in any centralized or decentralized setting, whatever leaves the client is vulnerable to attacks, right? So you have privacy issues that you have to take care. And then what you can also imagine is that the data that each of these clients gather are not the same. They come from different distributions. That's heterogeneous in nature. So what I'll be focusing on is to see how we can handle these two things in a very specific context of constraint optimization. So before that, two quick slides on what is heterogeneity. What I mean by heterogeneity is the following. So you have these clients, each of them gather data sets, but they are different in the following sense. Either the classes are different, they come from different class distribution, there is skewness in classes, or skewness in the feature space, or skewness in the quantity of data. So these are at a high level what heterogeneity would mean, but for me, I'll come back to this notation later on. What this basically means is that the gradients are not stochastic. So what typically happens is I have a data set, I sample a data set, I compute my gradient, I run a gradient descent method, right? So the stochastic gradient basically means that on average and expectation they converge to the true gradient. Now if there is heterogeneity, the distributions are different. So this is the iteration, the trait that I'm interested in. The distributions are different. So these gradients do not agree with each other, right? So each gradient is pointing in different directions. And when I do some kind of consensus, then I don't know where I go to, right? So that is formally what we mean by heterogeneity. And privacy, nothing much to add here. Although the data is not leaving the clients, you still transport models or gradients. And there is a possibility that you can infer about the data starting from the model or the gradients, right? So we want to avoid this. And the way that is typically done in this information theoretic sense is through this notion of differential privacy. So what this means is the following. Suppose I have two data sets which are adjacent by 1 point, say. Now, and there is a randomized mechanism that could be my optimizer that is trying to solve some optimization problem. The two data sets passed through this randomized mechanism are indistinguishable, right? So if they are epsilon indistinguishable with some delta here, the ratios of these probabilities are epsilon indistinguishable, then we say that they are epsilon delta differentially private. Okay, so that is the notion. And now one simple way to basically ensure differential privacy is that whenever a gradient or a model leaves the client, you perturb that, you deter that with some known calibrated noise, for example Gaussian noise. Okay? And of course more noise gives you better privacy. So you want this epsilon to be small, and that is controlled by this sigma, that is the amount of noise that you add. Okay? So that basically tells us how differentially private our model is, right? So that is the background of what most of the things that I need for this talk. So this is a problem setting. I want to solve this global optimization problem, minimize f with respect to x, such that x is in some constraint set. That is a standard constraint optimization problem. I have n clients. For the sake of this discussion, I will assume that each of these clients are solving the same optimization problem, which means that this f superscript I is little f, right? So for all the nodes, except that the data is different at each of these nodes. Okay? And C is a constraint set. Assume that to be convex and compact. Now, when you are training a machine learning model, you would like to regularize that model, have some structure in the model, for example, sparsity or low rankness whenever you are communicating the models across clients, because you want to basically have better communication overhead, or you want to learn models that are robust or fair. So that is where you would impose such constraints. So that's basically the context. Now what we want to do is we want to learn this, solve this problem P in a decentralized setting. I don't have access to all the data in one place, so I would like to use this notion of consensus and gossip, but keeping in mind that the data across clients are heterogeneous and guarantee differential privacy. I will discuss these two problems separately, but the combination of A and B would be trivial as we progress towards the end. Any questions so far? Is the context clear? Yes. That is difficult. I mean, under the notion of differential privacy, it is not. So you cannot basically denoise, right? That's the randomness you introduce. So you might know, you might learn the statistics of the noise, but not the exact realizations of the noise. Okay. Okay. So now some more background. I'm sure all of you know this. So how do you solve a constrained optimization problem? The standard approach that comes to your mind is, which I'll not take, of course, is the projected gradient descent. What you do in projected gradient descent, you do this gradient descent, G is the gradient, you go in the direction of the negative gradient, and you project orthogonally onto this projection set through this projection operator. Now, there is an alternative school of thought to solve this projection. I mean, instead of doing this projection to solve this constraint optimization problem, that is the Frank-Olfe method or the conditional gradient method, often also called as a projection-free method. What does it do? Slide is slightly dense. I'll tell you what are the advantages of this method. For certain type of constraint sets, particularly like polytopes, matroid constraints, solving the conditional gradient is much more cheaper compared to the projection based method, right? So that is the incentive for going behind the conditional gradient method. Okay. Now what does it do? It has two steps. It finds a descent direction in the constraint set by solving this linear minimization oracle, LMO in short. What does it do? You basically have a function that is differentiable, smooth. You take the first order Taylor of it, okay, and then you try to find a vector that is most aligned to this gradient vector, the constant term, you can ignore it for the optimization problem. You try to find a vector that is most aligned to it, but in the constraint set. Okay, that is going to give you the descent direction. Now, if it is like a simple polytope like what you see here, you're solving a linear program. The solution will be on one of the vertices, well-known result. Now, to compute the iterate, you take a convex combination of what you had before, the step and the previous iterator. This guarantees two things. One is computational gain, given the linear minimization oracle for not all constraint sets, but for many popular constraint sets. That is an easier problem to solve. You are basically solving an LP. And the second advantage is the iterates are always in the constraint set. Okay, S is in the constraint set, xk was in the constraint set. You take a convex combination, you get in the constraint set. And going back, if you don't have any constraints, what you're basically doing is the steepest descent. Yes, Salim. Okay. Yeah, so that is Frank-Wolfe, a very old method, right? So maybe, if I'm right, it's from the 40s, out of a master thesis, right? Nothing too complicated there. So we want to leverage this method, but of course in the stochastic setting, where you replace these gradients with a stochastic gradient. Yeah, so it's called, yeah, it's called projection free because of this property of the LP, right? So you can basically find the solution in a on the vertices, right? So that's the name. Any further questions? Why would I think? When? Yeah. So again, like not for all constraints. For starters, if you have a polytope, right? So then you basically have a nicer result, right? So basically, whenever you can solve this LP easily. And having said that, not all constraints would be as simple as a projection via LMO, right? So that is that is the thing one has to accept, right? So for example, many of these constraints, for example, whenever you have a low rank constraint, a nuclear norm constraint, then basically you don't have to do an SVD, do the soft thresholding. That is what a projection would do. But then you can do a rank 1 computation using the leading singular vectors. So that's what is given here in summary. What is Frank-Wolfe, especially for this low rank matrix completion type problems. The projection, the LMO is basically this rank 1 matrix that you have to compute via these leading singular vectors that one can compute easily instead of computing all the singular vectors. So some of the constraint sets, LMO is easier to compute, and we'll be focusing on those constraint sets. And the known result is, again, for a particular choice of the step size and so on and so forth, you can guarantee sublinear convergence. So that's about Frank-Wolfe. Yes. The optimum would not be in the interior, right? So it will always be in the vertex. So now the notation will be clear. F is the objective that is common across all the clients. X is the iterate. This is the random sampler that I have. I sample from that data set. That is what makes the objectives different across clients. Okay. So now, how do we handle heterogeneity? This is the proposal that we have. Just to have the vanilla method with IID data, you compute the step, that's the gradient. You do a consensus of the gradient with the local neighbors. Okay, you talk to your neighbors, you see what the local gradients are, you do a one-step consensus through this mixing matrix W, which is basically telling what the underlying topology is, and then you basically solve an LMO. So you are computing a new gradient that has information about the local neighborhood. You use that gradient to compute the step, and then you use the usual convex combination to compute the iterate, the local iterate. Now, when the data is not IID across nodes, then this would not make much sense, because each gradient would be pointing in different directions. They're not aligned, but then you are trying to get an average of those gradients, and you would get an arbitrary direction, which would not necessarily point towards the direction that you would like to go. So the proposal is the following. We call this as a slight modification to the LMO. It is the gradient aggregated LMO. So what we do is the following. We accumulate the gradients. We don't compute the average. So I have 3 neighbors. I collect the gradients from these 3 neighbors, and now when computing the step, the descent direction, what I do is the following. I introduce this constraint. What this constraint does is, I'm still finding a direction that is aligned to the negative gradient in the constraint set, but also see which of those gradients from my neighbors are negatively correlated. So I'm accounting for the gradient information from my neighbors. Okay? So what in a vanilla case, what you would do is you would only solve this without the constraint. But now what you're saying is, I have these gradients that are sitting in these rows of this G matrix. Now I'm finding the gradients, or I'm finding a descent direction in the constraint set that is also aligned to my gradient, to the gradients that are sitting in the neighbors. Okay? So now once you have this, this has information about the data that is in the neighborhood. Then after this, once you have Sk's, you simply do a convex combination with the Xk that you had previously. I have 2 pictures. Maybe this is a better picture to illustrate. So what this picture is basically telling is, if you have 2 points, gradients are opposite, pointing in opposite directions, if you simply do an LMO, you would diverge, and if you take care of this gradient information from the neighborhood, you would converge. That is what this picture is telling, but more better illustrated, I guess, here. So you have an L2 ball as a constraint set. Those are those circles that you see here in magenta, and this is like a least squares problem, so hence the concentric level sets that you see here. Now the iterate is that red dot, the magenta dot there. Now you have a local gradient which is pointing in this direction, so you would like to go in the direction of the negative gradient as far as that local client is concerned. You have 2 neighbors giving you G1 and G2 pointing in these 2 opposite directions. If you do a simple consensus, assuming that the weights are 1, you basically ignore the information from the neighbors because they are pointing. G1 is basically minus G2, that gets cancelled, and then you simply go in the direction of the local data. Right? So what that means is, say suppose you're solving this MNIST problem, each client has information about only 1 class label. Then you're basically optimizing for that label, right? You're ignoring all the other labels which that particular client doesn't have. So you're basically going in this direction. Now instead, what you would do with the proposed LMO is, now you would see, okay, which of the other 2 gradients are more aligned to my local gradient. So you try to take data from that, and you would get a direction that is along this line. So you would basically hit again the circumference of the L2 ball as a solution. Okay? So that's, I can picture what is going on. So this is a summary. Again, I think it's kind of a repetition of what I just said, but maybe worthwhile. So you replace the LMO with the gradient aggregated LMO by aggregating gradient information. So you just have gradients from the neighbors. You don't do consensus, but then you use those gradients while computing this. Now 2 things that we can say about this, or 2 questions that we can ask to begin with. Is that GA-LMO a feasible optimization problem to begin with? Does it have a solution? The result here says, without bothering you with the details, it says that the solution always exists, and the trivial solution can be easily shown to be always existing. The other interesting thing that we can show is, for LP norm constraints and L2 in particular, we have a better interpretation of what this GA-LMO is doing. And for L2, what this basically tells is the following. So you have a constraint optimization problem. The usual approach is to formulate it as an unconstrained optimization problem with a Lagrange multiplier. Mu is that Lagrange multiplier, and what this is telling you is how to weigh these gradients. Mu is a Lagrange multiplier. The optimal mu tells which gradient should I pick, right? So that is the interpretation of what is going on here. In addition to this, the more theory it's there in the paper. You can ask Robin if you're interested in. But what we show here is the following. You still retain the sublinear convergence 1 over k with this parameter alpha, which basically quantifies the heterogeneity, right? So that is the bottom line. You can show this for smooth convex functions. If you have strong convexity, you don't gain further, but non-convex, the convergence is slightly different with respect to the duality gap. That basically is the first order convergence. Again, we have sublinear convergence of order k, or 1 over k. So that's basically the theory that you get. Simulations, maybe I'll spend like a few seconds on this. What we show is that doesn't matter what type of an underlying topology you're using, as long as it's connected, you get convergence and you get better convergence with the proposed method, both on some simple tasks like lasso matrix completion to training a deep learning model, right? So those are the results that you have here. Again, like training a simple neural network on CFAR and MNIST data set, there's convergence. Basically, to have some regularized model at the output. But in the remaining time, I would like to discuss the differential privacy and the issues with differential privacy. You get the message from this slide. So suppose we are doing any decentralized optimization, including the Frank-Olfe update. I would like to have a certain structure in the model. It could be either a sparsity structure or a low rank structure in the model. Now, what differential privacy is suggesting is, to get this privacy guarantees, I need to perturb that model. Perturbing that model, I would lose the structure. The same would happen if I'm doing it in a distributed way or a centralized way, because suppose I have a sparse vector, you add noise, the sparsity is gone. Now you do averaging or consensus of these vectors, the structure is lost. The question is, how would I retain the structure but still ensure differential privacy? Okay. Now, the answer to that is the following. Instead of perturbing the iterates of the model, you go to the dual domain, and the dual vectors in this conditional gradient method is nothing but the gradients. So you don't perturb the model, but you perturb the gradients. And in addition, we do something known as a dual averaging, which is a standard technique in stochastic gradient methods, like it's called as a iterate averaging, for instance, or stochastic variance reduction methods. So you perturb the dual, and then you do an average. This kind of acts like a smoothing filter, where you are averaging out the noise, but at the same time you preserve the privacy requirements. And once you have this, you do a consensus on this averaged dual gradient. So what this picture suggests is basically the following. There are 3 curves here. One is without doing this dual averaging, you simply perturb, which basically hampers the structure, the sparsity is lost. The bottommost one without any hyphen acronyms here is basically like you don't care about differential privacy, so there's no perturbation. That is where the model is converging. But then with this dual averaging, you see that with dual averaging you converge, maintaining to the sparsity requirements that the unperturbed model had. Okay, so that's basically about differential privacy. The results are along the same lines. What this basically suggests is the following. The suboptimality gap is basically governed by 3 things. One is the error due to the consensus operation, non-availability of data at the central location. So there is one term that contributes to that. The other term due to stochasticity and differential privacy. And the other one is due to the consensus, right? So again, differential privacy. So the bottom line is we again get sublinear convergence, order 1 over k, but now within a ball of radius sigma. That is the noise that we add. These are the results again suggesting that, okay, what we do is good, right? So you basically apply this on MRI and these recommendation system data sets with low rank constraints and sparsity constraints. You maintain the structure of the model either via sparsity or the rank constraints while converging. Okay. So I guess that was the alarm for my time. That also brings me to the last slide. So what we discussed was, these were 2 things. One is the conditional gradient method, but decentralized version of a conditional gradient method, handling heterogeneity as well as privacy. There are more results along these directions, so that's basically Robin's PhD thesis. One of the issues that Salim touched upon was communication overhead, because you're talking to all of your neighbors, and in fact you need not do that, so you can do a smart way of doing consensus by basically sampling the neighbors whom you want to talk to, right? Because at some point the information is more or less there in the neighborhood, you need not revisit them each and every time. So there are more results along those lines. With that, thanks for waiting till the end. More details are there in these papers. Feel free to take a look at them. Thank you.
So we have time for a couple of questions. Yeah, Salim.
But yeah, so then, but you would only maintain your local neighbor, right? But also that's only in the one iteration. But the second iteration, you still have information from the two hop neighbors. No, because you're applying this consensus operator twice, right? It's like a W square that you apply. So if you write down unroll the iterations. About the ring with a very special case, and with a special case of a binary classification problem. Yeah. Yeah, sure, of course, yeah. But my guess is that still you have information, so you never cancel, right? You always have a local gradient. Maybe you would not get to an average, but you still have an iterate that would basically go to that local minima, right? Yes, that is what it would mean. Yeah. So there are many methods. For example, like so this would fall under the broader category of what is known as personalized federated learning, right? So one way is like, okay, I still want to respect my local model while taking care of the other models. The other one is like to basically take the relevant information, like projecting out. And what we are actually doing is kind of very similar in that sense, right? So you would still like project it onto the subspace of the gradients of the other local neighbors, right? So that is what it is going on there, right? But still, I mean, the whole point is like you would not, that's the gradients, but then what we are doing is we are computing the direction, the S, right? So you see the difference? Yes, yeah. So you don't directly, so in a, say in a, without any constraints in an unconstrained setting, you could basically deal with only gradients. But now this gradient is also giving me a step in the constraint set, right? So it's related in that sense, right? So but you still are in the subspace of, I think, yeah, it's basically in the row space of this G matrix, right?
There are no questions. Let's thank Sandeep.
So please don't leave. There's lunch arranged at the coffee hut outside. And before we go, can I invite all the speakers here on the stage for one quick last picture?
I'm going there.
You have to go on the stage.
On the stage, yeah. It's for the funding. Sorry. They couldn't come
last but not the least, thank you to all the organizers, Srinivas, Monmohan, Ashwarya, Tejaswini and Preetham for making this graphic, and all the other volunteers maybe I forgot it. Thank you. Give them a big
Yeah, also thank you to Parimal for organizing